toward a mass concentration, they might be repelled by voids, massive underdense regions that create gravitational imbalances. Tracking their trajectories over millions of years could help astronomers identify these hidden structures. Another possibility is that some of these galaxies could be escaping the universe itself. If space is expanding at an accelerating rate, certain objects may reach the cosmic event horizon, a boundary beyond which they recede faster than the speed of light due to spacetime expansion. From our perspective, they would fade into infrared darkness, never to be seen again. If one of these high-velocity galaxies breaks free from the cosmic web, the large-scale structure of interconnected galaxies and dark matter filaments, it may enter a completely empty region of space where gravitational interactions are minimal. Some physicists speculate that if spacetime has hidden topologies, wormholes, or interdimensional pathways, such a galaxy could theoretically exit into another universe, making it unobservable forever. If astronomers detect a stellar system that appears to be vanishing without explanation, it could provide the first direct evidence of such an event. While most of these galaxies are thought to move away from major structures, some might eventually collide with others at extreme velocities. A high-speed impact between two galaxies traveling at thousands of kilometers per second would release unimaginable amounts of energy, possibly creating an entirely new class of high-energy astrophysical events. Such a hypercollision could trigger the most violent starbursts ever observed, compressing gas into dense clouds that rapidly form new stars. However, it could also lead to the destruction of galactic structures, tearing apart stellar systems and forming long tidal streams of stars and gas stretching across millions of light-years. If one of these fast-moving galaxies collides with a normal galaxy, it might even lead to the formation of an ultramassive black hole, disrupting the gravitational balance of its surroundings. Detecting such an event would provide valuable insights into the limits of cosmic energy transfer and the behavior of galaxies under extreme conditions. Another strange idea is that some of these galaxies might not be what they seem. Certain anomalies in their motion could indicate that they are faint relics from the early universe. If a galaxy formed soon after the Big Bang and was ejected at high speed, its light might only now be reaching us, making it appear as though it exists in a different cosmic epoch. Others proposed that some of these high-velocity galaxies could be composed mostly of dark matter, making them nearly invisible except for their gravitational effects. If such formations exist, they could be drifting through space largely undetected, interacting only through gravity. Even more speculative is the idea that some of these fast-traveling galaxies might be holographic projections or manifestations of unknown physics, possibly revealing hidden dimensions or an emergent cosmic order. Future deep space surveys could help determine whether they are entirely normal objects or something far stranger. If an intelligent civilization evolved inside one of these high-velocity galaxies, its experience of the universe would be radically different from our own. Due to relativistic time dilation, time for the inhabitants of such a galaxy would slow down compared to the rest of the cosmos. If their stellar system were moving at a significant fraction of the speed of light, billions of years could pass for the outside universe while only a few thousand years pass for them. The motion of their galaxy through intergalactic space would also expose them to extreme cosmic radiation, which could require either advanced shielding technologies or biological adaptations to survive. If such a civilization were aware of their home galaxy's extreme velocity, they might attempt to influence its motion, either to slow it down or to direct it toward a particular region of the universe. If astronomers ever detect anomalous energy signatures or signals from a fast-moving galaxy, it could be evidence of an advanced civilization adapting to an extreme cosmic environment. Future telescopes such as the James Webb Space Telescope, the Vera Rubin Observatory, and new gravitational wave detectors will allow scientists to study ultrafast galaxies in greater detail. Among the most anticipated discoveries is the detection of the first relativistic stellar system, one moving at over 50% of the speed of light, which would challenge our understanding of gravity and dark matter. Another breakthrough could be finding a high-velocity galaxy that unexpectedly changes trajectory, suggesting the influence of unknown forces or even artificial manipulation. If one of these cosmic travelers is observed to vanish completely, it might provide the first observational evidence of cosmic gateways, wormholes, or higher-dimensional structures. Additionally, detecting a galactic hypercollision would reveal how energy transfers at the largest scales. The study of these extreme objects remains one of the most exciting frontiers in astrophysics. Whether they result from gravitational interactions, unknown cosmic forces, or even signs of intelligent engineering, such fast-moving galaxies push the boundaries of what we consider possible. As observational capabilities improve, we may soon uncover their true nature, possibly redefining our understanding of space, time, and the fate of the universe. If these high-speed galaxies exist in significant numbers, they may not be isolated anomalies but rather part of a greater cosmic pattern that has yet to be fully understood. Their existence challenges current astrophysical models, pushing the limits of our knowledge about gravity, cosmic expansion, and galactic evolution. They could also be linked to the formation of large-scale structures, revealing an unknown mechanism governing their motion at extreme velocities. One intriguing possibility is that these galaxies are not randomly propelled but instead follow gravitational highways formed by dark matter filaments. Some cosmologists propose that dark matter is distributed in a way that creates massive intergalactic superhighways, allowing certain stellar systems to move faster than expected. If this is true, these cosmic wanderers could provide crucial evidence about the large-scale structure and distribution of dark matter in the universe. Another theory suggests that fast-moving galaxies might be influenced by cosmic voids, vast empty regions with little to no matter. Instead of being pulled toward massive objects, these stellar formations could be repelled by these underdense regions, accelerating outward. Some scientists speculate that dark energy, the mysterious force driving the universe's expansion, might have local variations that push galaxies away rather than simply expanding space uniformly. If such galaxies are disproportionately found near cosmic voids, this could suggest that dark energy is more complex than previously thought. There is also the possibility that unknown fundamental forces accelerate these galaxies. While standard physics describes gravity as the dominant force at cosmic scales, alternative theories propose additional interactions affecting galaxies and clusters. If ultrafast galaxies accelerate in ways that cannot be explained by known gravitational effects, this could indicate the presence of a new fundamental force shaping the universe. Some researchers speculate that these stellar systems might be relics from an earlier phase of cosmic evolution. If physical laws or interactions between matter and dark matter differed in the early universe, certain galaxies may have been propelled to extreme velocities billions of years ago. This could mean that rather than being anomalies, these objects are remnants of a primordial event, offering insight into physics that no longer operates today. Another question is whether some of these galaxies might be artificial. If an advanced civilization had technology capable of manipulating gravitational fields, it could potentially control the motion of an entire galaxy. This could be done to escape a dangerous region of space, navigate toward a desired location, or even use galactic movement as a form of interstellar travel. If astronomers detect high-speed galaxies exhibiting controlled acceleration rather than purely natural motion, it could be a sign of large-scale engineering at work. Future observations will be crucial in determining whether these galaxies fit within known physical models or require new physics to explain their behavior. By analyzing their motion, astronomers may identify patterns revealing whether they travel randomly or as part of a larger cosmic structure. If they follow dark matter filaments, this could confirm the existence of gravitational highways shaping the universe. If they are concentrated near cosmic voids, this might indicate a previously unknown interaction between galaxies and dark energy. One of the most important breakthroughs could come from tracking the long-term trajectories of these cosmic speedsters. If their motion changes unexpectedly, defying known gravitational dynamics, it could suggest the presence of undiscovered forces. Additionally, if some of these galaxies appear to accelerate rather than simply maintaining constant speeds, this might indicate an unknown influence on their movement. Another groundbreaking discovery would be finding galaxies that appear to vanish. If a stellar system moves at extreme velocities and later disappears from observations, it might have crossed a cosmic boundary, such as the event horizon created by space expansion. This could provide direct evidence of galaxies escaping the observable universe, an idea long theorized but never confirmed. As observational technology advances, allowing astronomers to detect fainter and more distant objects, the study of ultra-fast galaxies will enter a new era. Next-generation observatories, including the Square-Kilometre Array and upgraded gravitational wave detectors, may uncover unknown aspects of galactic motion and interactions. If these high-velocity objects turn out to be more common than expected, it would suggest that the universe is far more dynamic than current models predict. Ultimately, these extreme galaxies could hold the key to solving some of cosmology's deepest mysteries. Whether they result from dark matter interactions, repulsion from voids, remnants of an ancient event, or even artificial constructs, their existence challenges fundamental astrophysical assumptions. Their study could not only redefine our understanding of galaxy evolution but also reshape our view of the universe itself. If these galaxies are more than just isolated anomalies, their movement could indicate that the universe's large-scale structure is far more active than previously thought. Their acceleration might be governed by unknown interactions between dark matter, dark energy, and intergalactic gravitational fields. If their motion cannot be fully explained by known mechanisms such as gravitational slingshots or black hole interactions, it could suggest that vast regions of space experience forces yet to be discovered. One of the most compelling possibilities is that these objects are responding to unknown gravitational waves or distortions in spacetime. If large-scale ripples in spacetime exist, perhaps caused by ancient cosmic events like the collision of supermassive black holes or remnants of a previous universe, they might subtly influence galaxy trajectories across billions of light-years. Future gravitational wave detectors could determine whether these galaxies are reacting to spacetime distortions beyond our current detection capabilities. Another intriguing question is whether these galaxies are linked to variations in dark energy. While dark energy is generally considered uniform, if high-speed galaxies tend to move toward or away from specific regions, it could mean that this force is unevenly distributed. Some parts of space might exert stronger repulsive forces, pushing entire galaxies to extreme velocities. If true, this would require a major revision of cosmological models, suggesting a far more complex expansion of the universe. It is also possible that these stellar formations reveal a new type of matter or interaction. If some galaxies accelerate in ways inconsistent with standard gravitational models, they might be affected by unknown particles or forces. For instance, if dark matter is not entirely passive but exhibits certain repulsive or dynamic properties under specific conditions, it might explain the unusual acceleration patterns observed. Alternatively, an undiscovered force acting at cosmic scales could first reveal its effects through these galaxies. A more radical idea is that these high-speed objects interact with hidden dimensions. Some string theory models propose that gravity may leak into additional spatial dimensions, causing unexpected deviations in galactic motion. If such galaxies are disproportionately found in certain regions of space, they might be interacting with higher dimensional structures, providing the first observational hint of extra dimensions. Another fascinating concept is whether ultrafast galaxies function as natural time machines. Due to relativistic effects, objects moving at extreme velocities experience significant time dilation, where time slows relative to the rest of the universe. If a galaxy were moving near the speed of light, an external observer might witness it aging much more slowly than surrounding cosmic structures. If civilizations exist within such galaxies, they could experience time on a vastly different scale, effectively becoming time travelers relative to the broader universe. The detection of these galaxies also raises fundamental questions about their long-term fate. If they continue accelerating, do they reach a threshold beyond which they can no longer interact with the rest of the universe? If so, does this imply the existence of cosmic escape routes, where matter can permanently exit the observable cosmos? If one of these stellar systems were to cross such a boundary, it might appear to slow and fade from view, eventually becoming undetectable. Observing such a disappearance would be among the most extraordinary discoveries in modern cosmology. Another consideration is whether ultrafast galaxies are indicators of an impending phase transition in the universe. If more of these stellar systems are found accelerating to extreme velocities over time, it could suggest a fundamental cosmic shift, possibly signaling a transition into a new state of physics. Some theoretical models propose that dark energy may eventually increase in strength, leading to the so-called Big Rip scenario, where galaxies, stars, and even atoms are torn apart as space expands at an accelerating rate. If these fast-moving galaxies are early signs of this process, they may be the first objects to reveal that the nature of the cosmos is evolving in ways we do not yet fully understand. As more advanced telescopes and computational models emerge, astronomers will be able to analyze high-velocity galaxies with unprecedented precision. If patterns emerge in their motion, they could reveal an underlying structure governing their trajectories. Some of these objects might also display unexpected compositions or energy signatures, suggesting interactions with forces beyond current understanding. Whether propelled by dark matter streams, gravitational distortions, or something even more exotic, these galaxies remain among the most enigmatic mysteries of the cosmos. The study of such extreme celestial objects has the potential to reshape our understanding of fundamental cosmic forces. Whether they are remnants of a previous cosmic cycle, indicators of hidden physics, or evidence of an undiscovered aspect of dark energy, their presence challenges the assumption that the universe is predictable and stable. Instead, they suggest a far more dynamic cosmos, where extreme motion and unknown interactions may one day redefine everything we know about space, time, and reality itself. If increasing numbers of fast-moving galaxies continue to be discovered, it could indicate that our understanding of the universe remains fundamentally incomplete. Their existence challenges traditional models of galaxy motion, hinting at unexpected forces at play or unknown interactions with cosmic structures. Future studies could determine whether these galaxies are simply anomalies or part of a larger, hidden pattern in cosmic evolution. One of the most crucial areas of research will be the long-term tracking of these cosmic travelers. If they exhibit variations in velocity or unexpected trajectory shifts, it could imply interactions with variable gravitational forces or invisible structures. Such deviations from expected motion would provide direct evidence of uncharted cosmic phenomena, potentially revealing undiscovered cosmic forces or gravitational anomalies. Advanced simulations and AI-driven analysis will be essential in mapping their paths and predicting their future movements. Another question is whether these galaxies interact differently with cosmic expansion. The accelerated expansion of the universe is attributed to dark energy, but hyperfast galaxies could provide new insights into how high-velocity objects behave within an expanding spacetime. If their movement deviates from standard cosmological expectations, it might suggest that space itself has hidden dynamics influencing their trajectories. Observing them over long time frames may offer clues as to whether space contains unknown factors that affect galaxies at extreme speeds. The role of dark matter in the motion of these high-speed stellar systems is another key question. If they exhibit velocities inconsistent with visible gravitational sources, it could suggest that dark matter plays a more active role in shaping their movement. Some theories propose that dark matter might not be entirely passive but could instead interact dynamically under specific conditions, forming invisible gravitational currents that direct galaxies along particular paths. If ultrafast galaxies are following these hidden flows, it would provide compelling evidence for the structure and behavior of dark matter on cosmic scales. There is also the possibility that these galaxies are linked to exotic astrophysical processes. Some hypotheses suggest the existence of previously unknown gravitational slingshot mechanisms capable of imparting immense velocity to entire stellar systems. If new classes of astrophysical events, such as interactions with rogue supermassive black holes or large-scale gravitational waves, are discovered, they could help explain why some galaxies achieve such extreme speeds. Investigating the environments around these objects could reveal whether they originate from regions of high gravitational instability. Another avenue of research is whether high-velocity galaxies represent a previously unknown evolutionary pathway for galactic systems. If some galaxies are ejected from dense clusters or experience prolonged high-speed motion through intergalactic space, they may undergo unique evolutionary processes. A galaxy moving at extreme velocity might lose its gas more rapidly, reducing its ability to form new stars. Over time, it could evolve into a dark, inactive system, devoid of significant star formation. If astronomers identify quiescent galaxies that appear to have once been high-speed objects, it could indicate that these stellar systems aged differently due to their extreme motion. Another intriguing possibility is that rapidly moving galaxies could serve as natural laboratories for testing relativistic physics on a galactic scale. Since objects moving at near-light speeds experience time dilation and other relativistic effects, their internal physics may subtly differ from stationary galaxies. If ultrafast galaxies exhibit unusual energy distributions or unexpected cosmic ray activity, they could provide an unprecedented real-world test of Einstein's theories at galactic scales. The potential for these galaxies to reveal hidden cosmic structures is another key area of study. If they consistently move toward or away from specific regions of space, it could suggest the presence of unseen mass concentrations, variations in dark energy, or even exotic gravitational anomalies. Some researchers speculate that hyperfast galaxies may act as natural probes of the universe's invisible framework, uncovering structures that otherwise remain undetectable. Large-scale surveys mapping their trajectories could provide new insights into the hidden architecture of spacetime. The ultimate fate of these galaxies remains uncertain. If one is moving at extreme speeds, does it eventually slow down due to cosmic interactions, or does it continue accelerating indefinitely? If some appear to gain velocity over time, it might indicate interactions with large-scale cosmic flows or even hidden dimensions. Conversely, if they eventually decelerate, it could suggest that intergalactic drag, dark matter interactions, or unknown gravitational effects gradually reduce their energy over billions of years. If any of these galaxies were observed to vanish from astronomical surveys, the implications would be profound. Such a discovery might suggest that certain galaxies are crossing into regions of space fundamentally different from our own, potentially supporting theories of cosmic gateways, wormholes, or even the multiverse. If a fast-traveling galaxy were to disappear without a trace, it would be among the most extraordinary astronomical findings in history, requiring a radical reconsideration of cosmic boundaries. As technology advances, the study of ultra-fast galaxies is likely to become one of the most significant fields in astrophysics. The ability to track them over millions or even billions of years could help resolve some of the biggest questions about the structure and evolution of the cosmos. Whether they reveal new forces, uncover exotic physics, or simply challenge our understanding of gravity on the largest scales, these extreme galaxies could hold the key to the next great discoveries in astrophysics. If these high-speed objects are part of a larger, hidden structure within the universe, their continued study may unveil aspects of the cosmos that remain undetected. They could be following unseen gravitational currents, responding to forces beyond our current understanding, or even moving toward a final destination beyond the limits of observable space. Their behavior might be signaling the presence of undiscovered cosmic phenomena, making them one of the most promising astrophysical mysteries of our time. One of the biggest questions surrounding ultra-fast galaxies is whether their trajectories are entirely random or if they exhibit patterns that suggest an underlying order. If their motion aligns with large-scale structures, such as cosmic filaments or dark matter streams, it would provide strong evidence that these stellar systems interact with an invisible framework shaping the movement of matter across billions of light-years. Future deep space surveys will be crucial in determining whether these galaxies follow specific paths or are simply the result of chaotic gravitational interactions. The possibility that hypervelocity galaxies are connected to large-scale cosmic expansion raises additional questions. If they are accelerating beyond expected limits, it could indicate that space itself does not expand uniformly. Some cosmologists propose that different regions of the universe may expand at varying rates due to fluctuations in dark energy density. If these high-speed galaxies are concentrated in areas of anomalous expansion, it might suggest that the acceleration of the universe is more complex than previously thought. Another potential factor influencing these fast-moving stellar systems could be unknown astrophysical events. While many are believed to have been ejected due to interactions with supermassive black holes or gravitational slingshots within dense clusters, there may be other unidentified mechanisms at play. If some galaxies reach extreme speeds without any apparent interactions, it could indicate the existence of new cosmic forces, undiscovered astrophysical explosions, or interactions with exotic forms of matter. A more radical hypothesis suggests that these galaxies might be revealing new physical laws that only become apparent on extremely large scales. In standard physics, galaxies should not be able to exceed certain velocity limits without external forces acting upon them. If some ultrafast galaxies are moving beyond these expected thresholds, it could suggest the presence of an unknown force or even a modification of general relativity that applies on the scale of galaxy clusters and beyond. If confirmed, this could revolutionize our understanding of gravity and possibly lead to a new theory that unifies relativity with quantum mechanics. Some physicists even speculate that hypervelocity galaxies might be linked to quantum effects on a cosmic scale. While quantum mechanics typically governs subatomic particles, some models suggest that quantum entanglement or other non-local effects might influence galactic motion under specific conditions. If high-speed galaxies exhibit unexpected correlations in their movement, it could be evidence that quantum processes play a role in shaping the structure of the universe at macroscopic levels. Another fundamental question is whether these cosmic wanderers represent a natural stage in galactic evolution or an extreme outlier. If they continue moving through intergalactic space, they may undergo drastically different fates compared to those remaining in galactic clusters. Over billions of years, such galaxies might lose their ability to form new stars as they deplete their gas supplies, ultimately evolving into dark, inactive systems drifting endlessly through the void. If astronomers identify evidence of such dead ultrafast galaxies, it could reveal entirely new processes governing the long-term fate of matter in the cosmos. The notion that hypervelocity galaxies might reveal the limits of the observable universe is another compelling possibility. If some move so fast that they eventually vanish from view, it might provide direct evidence that certain objects can reach cosmic horizons beyond which light can no longer return. If surveys show that these galaxies systematically fade from observations at certain distances, it could confirm that they are crossing into regions where spacetime itself becomes inaccessible. This would offer one of the strongest proofs that the universe has cosmic boundaries where information is permanently lost. Future discoveries might also include the first direct observation of a high-speed galaxy undergoing a major cosmic event, such as colliding with another galaxy or interacting with an unknown force. If a fast-moving system is observed to change direction unexpectedly, it could provide direct evidence of external influences shaping the universe at its largest scales. Detecting a hypervelocity galaxy accelerating in real time would be one of the most extraordinary findings in astrophysics, as it would suggest that an active mechanism is continuing to increase its speed. As technology advances, the study of these enigmatic galaxies will likely lead to some of the most profound discoveries in modern cosmology. Whether they are natural phenomena, remnants of a past cosmic event, or indicators of new physics, they challenge our current models of how the universe operates. Their motion may hold the key to unlocking secrets about dark matter, dark energy, cosmic expansion, and even the fundamental nature of space and time. Whatever the final explanation, these high-speed galaxies are among the most significant objects in the search for the deepest truths about the cosmos. If these hyperfast stellar systems continue to challenge existing astrophysical theories, their existence may force scientists to rethink fundamental aspects of cosmic evolution, gravity, and large-scale structure formation. These galaxies could provide insights into hidden cosmic mechanisms that remain undetectable through conventional means. Their study might ultimately lead to breakthroughs in understanding the true nature of dark matter, the effects of cosmic expansion, and the possible existence of previously unknown forms of energy or matter. One of the most significant research areas will be analyzing the environments from which high-velocity galaxies originate. If they are preferentially found in specific cosmic structures, such as dense galactic clusters, cosmic voids, or regions with unusually high dark matter density, it could reveal the conditions necessary for their formation. If these galaxies are disproportionately located in certain regions, it may indicate that large-scale gravitational flows, dark matter interactions, or even quantum effects play a role in their acceleration. Another crucial avenue of research involves the internal structure of ultrafast galaxies. If these objects move at extreme speeds through intergalactic space, their internal dynamics might differ significantly from those of stationary galaxies. For example, their gas clouds may be more compressed due to their rapid motion, potentially leading to unique star formation processes. Alternatively, they may lose their interstellar gas at an accelerated rate due to interactions with the intergalactic medium, causing an early shutdown of star formation. If hypervelocity galaxies display significantly different compositions or evolutionary paths, it could provide new insights into the long-term effects of high-speed motion on galactic evolution. A more speculative yet intriguing idea is that these fast-moving galaxies may be interacting with exotic forms of matter or energy that have yet to be identified. If some exhibit unexplained acceleration, it could suggest the presence of previously unknown interactions with dark matter or dark energy. Some theories propose that dark matter might not be entirely passive but, under rare conditions, could exert repulsive forces or interact with normal matter in unexpected ways. If these galaxies move in patterns inconsistent with known gravitational forces, they could provide the first observational evidence of such an interaction. Another question is whether their extreme motion affects their gravitational influence on surrounding space. General relativity predicts that massive objects moving at high velocities can distort spacetime, potentially generating gravitational waves. If ultrafast galaxies are massive enough and moving fast enough, they might produce detectable gravitational disturbances. Future gravitational wave observatories could potentially detect these signals, offering a new way to study these objects and their interactions with the universe. The idea that hypervelocity galaxies might be linked to new aspects of cosmic expansion is another emerging area of interest. While dark energy is considered responsible for accelerating the universe's expansion, its properties remain mysterious. If fast-traveling galaxies move in ways that correlate with variations in cosmic expansion, it could indicate that dark energy is not uniform but instead varies across space and time. This would suggest a more dynamic, evolving universe than previously believed. There is also speculation that some ultrafast galaxies might be influenced by interactions with undetected ultramassive black holes. If a galaxy were to pass close to an extraordinarily massive black hole, far beyond those currently observed, it could experience an extreme gravitational slingshot effect, reaching velocities much greater than expected. Discovering such an event would challenge assumptions about black hole mass limits and their role in shaping galactic motion. Ultimately, the study of hypervelocity galaxies may uncover fundamental truths about the universe's large-scale structure, unknown cosmic forces, and the hidden nature of spacetime itself. As research continues, these extraordinary objects may reveal that the cosmos is far more dynamic and complex than we ever imagined. Another unexplored possibility is whether ultrafast galaxies are linked to large-scale cosmic turbulence. Some cosmologists propose that the universe contains vast, swirling flows of matter, driven by gravitational interactions across billions of light-years. If such turbulent motions exist, These high-velocity stellar systems might be following these currents, much like how oceanic flows shaped the movement of ships on Earth. Confirming the existence of such large-scale gravitational streams could offer new insights into the dynamics of galaxy motion and reveal that the universe is far more fluid and dynamic than previously assumed. A truly radical hypothesis is that hypervelocity galaxies are related to hidden cosmic gateways or wormholes. If space contains natural shortcuts through higher dimensions, certain galaxies might be ejected at extreme velocities upon interacting with these structures. While wormholes remain theoretical, some models predict that such objects could generate gravitational anomalies capable of launching stellar systems into intergalactic space at extraordinary speeds. If some high-speed galaxies exhibit characteristics suggesting an origin from an unknown source, it could provide indirect evidence for the existence of these enigmatic structures. The long-term fate of these fast-moving celestial objects remains an unresolved question. If they continue moving at extreme velocities, do they eventually leave the observable universe? Could they be traveling toward a region of space with fundamentally different physical properties? If some hyperfast galaxies disappear from future observations, it might suggest that they are entering a domain where the laws of physics behave differently, offering potential clues about cosmic boundaries. Conversely, if these galaxies eventually slow down, it could indicate the presence of an unknown cosmic drag force, possibly related to interactions with dark matter or intergalactic plasma. Future telescopic missions, such as the Next Generation Extremely Large Telescope (ELT), and upcoming space observatories, will be crucial in studying these galaxies at unprecedented levels of detail. These advanced instruments will allow astronomers to examine their light signatures, gravitational influences, and motion patterns with far greater precision. If some high-velocity stellar systems display unexpected energy distributions, relativistic time dilation effects, or unexplained spectral shifts, it could provide direct evidence of new physics. Another avenue of research will involve determining whether some ultrafast galaxies show signs of artificial manipulation. If an advanced civilization possessed the ability to influence the motion of an entire galaxy, it might leave detectable signatures, such as precise, unnatural acceleration patterns. If these objects are observed changing course in ways that defy natural gravitational interactions, it could indicate an engineered cosmic event on an unimaginable scale. Additionally, if any of these galaxies emit anomalous energy outputs or unusual radiation signatures, it might suggest the presence of technological influences beyond our current understanding. As research into these mysterious galaxies progresses, their study could have implications beyond astrophysics. If they reveal new properties of gravity, dark matter, or cosmic expansion, it could reshape our understanding of the universe's structure and evolution. If some high-speed galaxies exhibit characteristics suggesting hidden dimensions, unknown forces, or artificial control, they could represent the first observable evidence of phenomena challenging modern physics. Whatever the ultimate explanation, these extreme galaxies remain a profound mystery that may hold the key to some of the deepest secrets of the cosmos. If these hyperfast stellar systems continue to be a focal point of astrophysical research, their study may ultimately lead to groundbreaking discoveries about the very fabric of reality. Their extreme motion challenges conventional astrophysical theories and raises profound questions about cosmic evolution, the true nature of spacetime, and the existence of unknown forces. The deeper astronomers investigate, the more they may uncover about the unseen structures governing the universe. One of the most urgent priorities for future research is mapping the precise distribution of these galaxies throughout the cosmos. If they cluster in specific regions or align with large-scale cosmic filaments, it could suggest that they are being influenced by a hidden gravitational framework. If, however, their distribution appears random, it might indicate that their acceleration results from individual astrophysical events rather than large-scale cosmic forces. Resolving this question could determine whether these galaxies are the product of known gravitational interactions or if they point to an unexplored mechanism shaping the universe. Another critical area of research will involve analyzing the spectra of high-velocity galaxies to determine whether they exhibit unexpected energy distributions or relativistic distortions. If some are traveling at significant fractions of the speed of light, they should experience measurable time dilation effects, where internal processes, such as star formation and supernova explosions, occur at different rates compared to normal galaxies. Observing these relativistic distortions would provide one of the most direct tests of Einstein's theories on galactic scales, refining our understanding of how extreme motion influences cosmic structures. One of the more speculative but intriguing ideas is that ultrafast galaxies might not be randomly ejected, but instead moving toward a destination. If these galaxies appear to accelerate toward a common region, it could suggest that they are being drawn toward an unknown attractor. Some cosmologists propose that massive, undiscovered concentrations of dark matter or even hidden spacetime structures may be exerting influence. If hypervelocity galaxies follow similar trajectories, it could provide evidence for unseen mass concentrations or new physics governing large-scale galactic motion. Another possibility is that these galaxies might serve as natural tests for modified gravity theories. Some physicists propose that gravity behaves differently at extreme distances or under high-velocity conditions, leading to alternative models such as MOND, modified Newtonian dynamics, or emergent gravity. If ultrafast galaxies deviate from expected motion based on standard general relativity, it could indicate that gravity itself requires modification, potentially leading to a new understanding of fundamental physics. If hyperfast galaxies continue to challenge standard cosmology, their study may lead to a fundamental rethinking of how galaxies move and interact on the largest scales. Their motion could provide indirect clues about the nature of dark energy, the role of dark matter, and even whether hidden dimensions influence cosmic structure formation. The continued search for these enigmatic objects could ultimately reshape astrophysics, revealing that the universe is far more complex, dynamic, and interconnected than we currently perceive. The potential role of dark energy in accelerating ultrafast galaxies remains an area of active exploration. While dark energy is generally thought to act uniformly across the cosmos, some theories propose that it may exhibit localized variations, creating hot spots where the expansion of space is stronger. If these high-velocity stellar systems tend to originate from or move toward regions with dark energy fluctuations, it could suggest that dark energy is not merely a passive background force but instead plays a dynamic role in galactic motion. Another unexplored avenue is whether hypervelocity galaxies are remnants of a past cosmic event, such as a large-scale gravitational disturbance that occurred billions of years ago. Some models suggest that during the early universe, interactions between quantum fields and cosmic inflation could have created regions of extreme motion, ejecting galaxies at high speeds. If these fast-moving galaxies are disproportionately found at certain redshifts corresponding to specific cosmic epochs, it might indicate that their motion was influenced by primordial energy conditions rather than recent gravitational interactions. One of the most radical hypotheses is that these rapidly moving celestial objects result from interactions with hidden dimensions of spacetime. Some string theory models propose that our universe is embedded in higher dimensional space, and under certain conditions, gravitational interactions with these extra dimensions could impart unexpected accelerations to massive objects like galaxies. If ultrafast stellar systems exhibit motion that cannot be explained by known physics, it could be the first observational evidence that extra dimensions have measurable effects on the universe. Another speculative yet increasingly discussed idea is whether some high-speed galaxies might have been artificially manipulated. If an advanced civilization had the ability to control gravitational forces on a galactic scale, it might be able to move its home galaxy or even entire star systems to escape a cosmic catastrophe, avoid hostile forces, or facilitate intergalactic travel. While this remains speculative, the discovery of a fast-traveling galaxy with unexpected energy outputs, unusual structural patterns, or signs of controlled acceleration would be one of the most extraordinary findings in astronomy. A crucial test for understanding these mysterious objects will be whether any are observed actively accelerating in real time. If a galaxy is detected with a measurable increase in velocity over observational periods, it would suggest that an unknown force or mechanism is continually acting upon it. Observing such an effect would be unprecedented, providing direct evidence of forces beyond conventional gravity shaping large-scale cosmic structures. As observational techniques improve, astronomers will also attempt to determine whether hypervelocity galaxies evolve differently compared to other galaxies. If they experience higher rates of stellar evolution, black hole activity, or cosmic ray emissions, it could suggest that extreme motion influences their internal processes. If these fast-traveling galaxies appear systematically younger or older than expected based on their environments, it might indicate that high-speed motion alters the long-term evolution of galaxies in unexpected ways. One of the biggest open questions remains whether ultra-fast galaxies are a rare phenomenon or if they are far more common than currently believed. If future deep-field surveys reveal large numbers of these objects, it might indicate that our current models of galaxy motion need revision. If, however, they remain rare outliers, it could suggest that their formation requires highly specific conditions that occur only in exceptional circumstances. If any hypervelocity stellar systems disappear from future observations, it could provide the strongest evidence yet that the universe contains boundaries or hidden structures that certain objects can cross. If a fast-moving galaxy were to vanish completely, leaving no detectable remnants, it might support theories suggesting that hyperspeed objects can enter regions of space that operate under fundamentally different physics. Detecting such an event would require long-term monitoring and precise measurements of galactic motion over decades or even centuries. Future space missions, including next-generation gravitational wave detectors, advanced infrared telescopes, and AI-driven sky surveys, will play a critical role in deepening our understanding of these enigmatic celestial objects. If these technologies reveal new and unexpected properties about hypervelocity galaxies, it could revolutionize our knowledge of cosmic motion, spacetime, and the hidden forces shaping the universe. Ultimately, these mysterious high-speed objects may hold the key to answering some of the deepest questions about the cosmos. Whether driven by dark matter flows, influenced by cosmic expansion, or propelled by unknown physics, their motion challenges everything we know about the fundamental laws governing the universe. The next discoveries in this field may not only transform our understanding of galaxy dynamics but could also provide insights into the ultimate fate of the universe itself. If ultrafast galaxies continue to reveal unexpected properties, their study may offer the first observational evidence for entirely new cosmic phenomena. These galaxies, moving at extreme velocities through the vastness of intergalactic space, could be the key to unlocking secrets about dark matter, dark energy, the fabric of spacetime, and the fundamental limits of physics. As research progresses, astronomers must develop more precise observational techniques, advanced computational models, and new theoretical frameworks to fully comprehend what drives their motion and what their existence implies for the nature of the universe. One of the most critical areas of future research will be determining whether hypervelocity galaxies exhibit anomalies in their gravitational interactions. If these galaxies move in ways that defy conventional gravitational dynamics, it could indicate the presence of additional gravitational forces that only act at extreme velocities. Some physicists have proposed that gravity may behave differently on cosmic scales than it does within galaxies, suggesting that ultrafast stellar systems could provide an experimental test for alternative gravity models, such as emergent gravity or theories involving extra dimensions. If some high-speed galaxies experience gravitational shifts or unexplained accelerations, it could suggest that they are interacting with forces beyond our current understanding. These findings could ultimately reshape modern astrophysics, revealing hidden aspects of gravity, the role of dark matter, and even the existence of unknown cosmic forces guiding the motion of galaxies at the largest scales. Another possibility is that ultrafast galaxies are interacting with cosmic structures that remain invisible to conventional observation. The existence of dark matter streams, gravitational corridors, or cosmic superhighways has been theorized, but direct evidence remains elusive. If these high-velocity stellar systems follow precise paths that align with unseen gravitational frameworks, it could indicate that they are being influenced by vast networks of gravitational fields shaped by dark matter. This would provide some of the strongest evidence yet that dark matter is not merely a passive background component of the universe but an active force shaping the motion of galaxies across intergalactic distances. The nature of dark energy and its role in accelerating hypervelocity galaxies remains an open question. If dark energy is not a uniform force but instead fluctuates across space, it could create regions where galaxies experience additional acceleration. If these fast-traveling galaxies are concentrated in zones of heightened dark energy activity or near pronounced spacetime distortions, it might indicate that dark energy is dynamic rather than constant. Such a discovery would represent a major shift in our understanding of cosmic expansion, suggesting that the universe's accelerated growth is far more complex than previously assumed. A major challenge in studying these mysterious objects is determining whether they are truly moving at extreme velocities relative to the rest of the cosmos or if their apparent motion is influenced by unknown distortions in spacetime. Some theoretical models propose that spacetime itself may contain warps or folds, allowing galaxies to appear to move at high speeds while actually following curved paths through the universe. If ultrafast stellar systems are found to be bending around unseen gravitational distortions, it could provide evidence that space itself is structured in ways that challenge classical relativity. Another possibility is that hypervelocity galaxies serve as indicators of large-scale cosmic phase transitions. Some theories suggest that the universe undergoes slow but fundamental shifts in its physical properties over time. If these high-speed galaxies are accelerating due to changes in the underlying fabric of spacetime, they might be early signs that the universe is entering a new evolutionary phase. Certain models propose that the universe could eventually transition into a different physical state, altering the fundamental constants of physics. If ultrafast stellar systems are responding to such a shift, it could be a precursor to a major cosmic event. There is also speculation that these fast-moving celestial objects may result from interactions with exotic astrophysical structures, such as primordial black holes, ultramassive dark matter clusters, or even cosmic strings, hypothetical spacetime defects that could exert extreme gravitational forces. If high-speed galaxies are observed moving away from certain regions at extraordinary velocities, it might indicate that they have been affected by the gravitational pull of an unseen cosmic entity. Discovering the source of such interactions could lead to the identification of entirely new classes of astrophysical objects. The long-term fate of these ultra-fast galaxies remains one of the greatest mysteries in astrophysics. If they continue accelerating indefinitely, do they eventually leave the observable universe? If so, what happens to them beyond the cosmic event horizon? If some hypervelocity stellar systems are crossing into regions where physical laws function differently, it could suggest that the universe has boundaries, hidden dimensions, or even transition zones that separate distinct cosmic regions. If any of these fast-moving galaxies disappear entirely, it might serve as evidence that they have entered a realm where information cannot return to us. Future space-based observatories will be essential for tracking these high-speed objects over long periods to determine whether they are following predictable trajectories or if their motion is influenced by unknown cosmic forces. AI-driven sky surveys could detect patterns in their motion that might hint at large-scale cosmic structures or interactions with invisible mass concentrations. If unexpected acceleration trends are observed, it could suggest that these galactic travelers are experiencing forces that defy conventional models of cosmic motion. One of the most speculative but intriguing possibilities is that hypervelocity galaxies might have been influenced by intelligent intervention. While this idea remains far outside mainstream astrophysics, some theorists have suggested that a sufficiently advanced civilization could manipulate gravitational forces on a galactic scale. If some ultrafast stellar systems show signs of unnatural motion, precise acceleration, or patterns inconsistent with natural astrophysical processes, it might indicate an engineered event. Detecting anomalous energy emissions or unexplained course adjustments in high-speed galaxies would be among the most profound discoveries in the history of science. Another crucial test will be whether these fast-moving galaxies experience significant internal changes due to their motion. If traveling at extreme velocities through intergalactic space affects their ability to form new stars, retain interstellar gas, or sustain long-term stability, it could suggest that hypervelocity motion actively reshapes galactic evolution. If certain high-speed stellar systems are found to be devoid of young stars or have unusually disrupted structures, it might indicate that their motion is altering them over time. If these ultra-fast galaxies continue to be discovered in greater numbers, it could indicate that they are not rare anomalies but rather a fundamental component of cosmic evolution. If their numbers are found to be increasing over time, it might suggest that the conditions leading to their formation are becoming more common as the universe evolves. If they remain relatively rare, it could mean that they are the result of exceptional circumstances, making them valuable cosmic laboratories for studying extreme physics. Ultimately, these high-speed objects represent one of the most fascinating frontiers in astrophysics. Their existence challenges long-standing assumptions about cosmic motion, gravity, and the large-scale forces shaping the universe. Whether they are natural outliers, the result of unknown interactions, or indicators of new physics, they hold the potential to redefine our understanding of the cosmos. The next major discoveries in this field may provide insights not only into how galaxies move but also into the deeper mysteries of space, time, and the fundamental nature of reality itself. If these ultra-fast stellar systems continue to defy conventional astrophysical models, their study may reveal deeper truths about the forces governing the cosmos. These galaxies, moving at extraordinary velocities, may be signaling the presence of unknown interactions that have remained undetected. Their extreme motion could be linked to dark matter flows, gravitational anomalies, hidden dimensions, or even cosmic phase transitions that reshape the universe over vast timescales. One of the most important questions surrounding these high-velocity objects is whether they are accelerating due to a singular event, such as an interaction with a supermassive black hole, or if their motion is being continuously influenced by an external force. If their speeds remain constant or gradually decrease due to interactions with intergalactic plasma, it would suggest that they are remnants of past gravitational interactions. However, if some hypervelocity galaxies are found to be gaining speed, it could indicate that an unknown force is still acting upon them, requiring entirely new physics to explain their continued acceleration. If future gravitational wave observatories detect disturbances linked to these galaxies, it could provide a new method for studying the interplay between high-speed motion and the curvature of spacetime, bringing us closer to understanding the true nature of the cosmic web and the hidden forces shaping the universe. The relationship between ultra-fast galaxies and dark energy remains an area of growing interest. If dark energy is responsible for the acceleration of the universe's expansion, could it also be exerting a localized influence on the motion of individual stellar systems? Some models suggest that dark energy may not be a uniform force but could fluctuate, creating zones of increased acceleration. If hypervelocity galaxies are found in specific regions where dark energy appears stronger, it might indicate that the expansion of the universe is not as smooth and uniform as previously believed. Another possibility is that these high-speed galaxies represent an entirely new category of astrophysical objects, stellar systems evolving under extreme conditions, potentially giving rise to unexpected physical effects. If these galaxies experience rapid gas loss as they travel through intergalactic space, they may undergo unique evolutionary processes, leading to the formation of exotic stellar populations or large-scale structural distortions. If ultra-fast galaxies differ significantly in composition or star formation rates from normal galaxies, it could indicate that extreme motion alters galactic evolution in ways we have yet to fully explore. Some cosmologists propose that hypervelocity stellar systems could be part of a larger cosmic cycle. If the universe undergoes periodic transformations, with regions of space experiencing gravitational shifts over time, then these fast-moving galaxies might be the first observable evidence of a large-scale cosmic phase transition. If high-speed galaxies are preferentially found at certain cosmic distances, corresponding to different eras in the universe's history, it could suggest that their motion is linked to changes in the fundamental structure of spacetime itself. There is also the possibility that these extreme stellar systems provide indirect evidence of quantum effects at cosmological scales. While quantum mechanics is typically confined to the microscopic world, some theories suggest that quantum fluctuations could influence large-scale cosmic structures. If ultrafast galaxies exhibit statistical correlations in their motion that defy classical explanations, it could indicate that quantum entanglement or other quantum effects play a role in shaping galactic trajectories on the largest scales. One of the biggest unanswered questions is whether these hypervelocity galaxies are isolated anomalies or part of a broader trend. If future deep field surveys reveal that more galaxies are reaching extreme velocities, it might indicate that the universe is experiencing a shift in its large-scale gravitational balance. If, on the other hand, these objects remain rare outliers, it could suggest that their formation depends on specific, extreme conditions, making them valuable test cases for studying high-energy cosmic interactions. Another area of ongoing research is whether these fast-traveling galaxies might be crossing into regions of the universe where physics behaves differently. If some galaxies move toward zones where their light becomes increasingly redshifted and eventually vanishes, it could be a sign that they are approaching cosmic boundaries beyond which information cannot return. If a hypervelocity stellar system were to disappear completely, it would be one of the strongest pieces of evidence yet that the universe contains regions where space, time, or fundamental laws undergo profound transformations. One of the most speculative yet intriguing possibilities is that these high-speed galaxies may have been influenced by intelligent intervention. While this remains highly theoretical, if a civilization were capable of controlling gravity on a galactic scale, it might possess the ability to move entire star systems or even entire galaxies. If some ultrafast stellar systems exhibit unnatural patterns of motion, precise velocity shifts, or energy outputs that do not match known astrophysical processes, it might suggest deliberate acceleration. While such a discovery would be extraordinary, it would also redefine our understanding of advanced technological possibilities in the cosmos. Ultimately, the study of these mysterious high-speed galaxies represents one of the most exciting and unexplored frontiers in modern astrophysics. Whether they are relics of past cosmic events, indicators of new physics, or evidence of unknown cosmic forces, they challenge the very foundations of our understanding of the universe. The next generation of telescopes, AI-driven sky surveys, and advanced gravitational wave detectors may provide the first definitive answers about these enigmatic objects. If these ultrafast galaxies are natural phenomena, their study could refine our knowledge of galactic motion, dark matter interactions, and cosmic expansion. If they are driven by unknown physics, they could lead to entirely new theories that reshape how we understand gravity, space, and time. And if, in the most extreme scenario, they are found to be influenced by intelligent manipulation, it would mark one of the greatest discoveries in the history of science. As research into these high-speed stellar systems continues, the potential for groundbreaking discoveries remains vast. Whether they hold the key to the secrets of dark matter, quantum gravity, or hidden cosmic architectures, they are among the most fascinating and mysterious objects in the observable universe. The answers they provide may not only change our understanding of galaxies but could also redefine the nature of reality itself. These hypervelocity stellar systems remain one of the most enigmatic mysteries of the cosmos, challenging our understanding of gravity, dark matter, and the fundamental forces shaping the universe. Whether they are remnants of past cosmic events, indicators of unknown physics, or signs of vast, hidden structures, their motion defies conventional explanations. As future telescopes and AI-driven surveys continue to track their trajectories, they may reveal profound insights into spacetime, cosmic expansion, and the ultimate fate of the universe. Whatever the final answer may be, the study of ultrafast galaxies has the potential to reshape our perception of reality itself. Creating a text of 100,000 characters requires significant effort. It'll provide you with a long, detailed, and engaging text about the Whirlpool Galaxy, packed with scientific details and research, aiming to captivate the audience. Let me start, and feel free to guide me if you'd like adjustments. The Whirlpool Galaxy, catalogued as Messier 51, M51, and often referred to as NGC 5194, stands as one of the most iconic and visually stunning examples of a spiral galaxy in the observable universe. Nestled within the relatively small constellation Canes Venatici, this celestial masterpiece has long been a subject of fascination for both amateur stargazers and professional astronomers. It represents a quintessential example of a grand design spiral galaxy, with its sharply defined arms and luminous core serving as a beacon for those studying galactic evolution and interactions. Located approximately 31 million light-years away from Earth, the Whirlpool Galaxy is relatively close in cosmic terms, making it a prime target for telescopic observations. Its visual magnitude of 8.4 renders it visible through small telescopes, while its intricate details can be fully appreciated with more advanced equipment. The galaxy spans roughly 76,000 light-years across, making it slightly smaller than the Milky Way, yet its beauty and complexity are no less impressive. One of the most intriguing aspects of the Whirlpool Galaxy is its interaction with its smaller companion, NGC 5195. This satellite galaxy, which is physically connected to M51 via a luminous bridge of stars and gas, has profoundly influenced the Whirlpool structure. The gravitational forces between these two galaxies have induced significant tidal effects, resulting in the formation of the Whirlpool's distinctive, well-defined spiral arms. These arms are not merely visual features, they are regions of intense star formation, often referred to as stellar nurseries. Massive clouds of hydrogen gas within these arms collapse under gravity to form new stars, some of which are among the brightest and most short-lived in the universe. The Whirlpool Galaxy has been extensively studied in multiple wavelengths of light, from radio to X-rays, revealing a wealth of information about its composition, dynamics, and history. Observations in the ultraviolet and optical spectra highlight the regions of active star formation, where young, hot stars illuminate surrounding gas clouds. Infrared studies, such as those conducted by the Spitzer Space Telescope, have provided insights into the distribution of cooler interstellar dust, which serves as the raw material for future generations of stars. Meanwhile, X-ray observations, particularly those made by the Chandra X-ray Observatory, have identified numerous high-energy phenomena within the galaxy, including black holes, neutron stars, and supernova remnants. The central region of the Whirlpool Galaxy is of particular interest to astronomers. Like most large galaxies, M51 hosts a supermassive black hole at its core. This black hole, with a mass estimated to be millions of times that of the Sun, exerts a profound influence on its surroundings. Material falling into the black hole forms an accretion disk, where gravitational and frictional forces heat the gas to extreme temperatures, causing it to emit radiation across the electromagnetic spectrum. These emissions make the galactic nucleus a bright source of X-rays and radio waves, offering a glimpse into the otherwise hidden processes occurring near the event horizon. The interaction between M51 and NGC 5195 has not only shaped the Whirlpool's spiral arms but also triggered waves of starburst activity. As the smaller galaxy passes through the disk of M51, it compresses the gas and dust within the spiral arms, leading to the rapid formation of stars. This process is thought to be responsible for the unusually high rate of star formation observed in the Whirlpool Galaxy. Such interactions are a common feature in the life cycles of galaxies and are believed to play a crucial role in their evolution. The Whirlpool Galaxy has also been a fertile hunting ground for supernovae, with several notable events recorded in recent decades. These stellar explosions, marking the violent deaths of massive stars, are not only spectacular to observe but also serve as laboratories for studying the physical processes governing the universe. Supernovae eject vast amounts of heavy elements into the interstellar medium, enriching future generations of stars and planets. They also produce neutrinos, elusive subatomic particles that provide insights into the fundamental forces of nature. One of the most remarkable aspects of studying the Whirlpool Galaxy is the ability to observe the processes of galactic interaction and evolution in real time. The gravitational dance between M51 and NGC 5195 is a dynamic process that unfolds over millions of years, offering astronomers a unique opportunity to study the stages of galactic collisions and mergers. These interactions are not merely chaotic, they are also creative, giving rise to new structures and triggering bursts of star formation that breathe new life into the galaxies involved. Technological advancements in telescopes and observational techniques have played a key role in deepening our understanding of the Whirlpool Galaxy. Instruments such as the Hubble Space Telescope have provided high-resolution images that reveal the intricate details of its spiral arms and star-forming regions. Ground-based observatories equipped with adaptive optics systems have also made significant contributions, enabling astronomers to overcome the blurring effects of Earth's atmosphere. Furthermore, radio telescopes have mapped the distribution of neutral hydrogen gas within M51, shedding light on the galaxy's large-scale structure and dynamics. The study of the Whirlpool Galaxy extends beyond its immediate vicinity. As a nearby example of a grand design spiral galaxy, M51 serves as a benchmark for understanding similar systems throughout the universe. Its well-defined features make it an ideal target for testing theories of galactic structure and dynamics, while its ongoing interaction with NGC 5195 provides valuable insights into the role of mergers and tidal forces in shaping galaxies. Researchers have also used the Whirlpool Galaxy as a testing ground for advanced computational models of galaxy formation and evolution. By simulating the gravitational interactions between M51 and its companion, scientists can reproduce the observed structures and gain a deeper understanding of the physical processes involved. These models not only enhance our knowledge of the Whirlpool Galaxy but also improve our ability to interpret observations of more distant and less well-resolved systems. The Whirlpool Galaxy has inspired countless scientific discoveries and remains a source of wonder and curiosity. Its striking appearance, with its luminous core, sweeping arms, and dynamic interactions, captures the imagination of all who observe it. Whether through the lens of a telescope or the pages of a scientific paper, M51 invites us to ponder the intricate and interconnected nature of the cosmos. As technology continues to advance, the Whirlpool Galaxy will undoubtedly yield even more secrets, enriching our understanding of the universe and our place within it. This majestic cosmic structure, often referred to as the spiral wonder of Cain's Venatici, captivates observers not only with its aesthetic brilliance but also with the wealth of scientific knowledge it holds. The celestial pair of the Grand Vortex Galaxy and its smaller companion, the stellar bridge neighbor, NGC 5195, represents a dynamic system where the forces of gravity orchestrate a cosmic ballet. This dance between the two entities serves as a living example of how galactic collisions shape and redefine the universe on massive scales. The galactic whirlpool system, as it is sometimes called, has been pivotal in advancing our understanding of starburst phenomena. The regions within its prominent spiral arms, saturated with hydrogen alpha emissions, highlight zones where stellar nurseries thrive. Here, vast molecular clouds collapse under gravitational forces, birthing stars that are not only young. The intense ultraviolet radiation from these newborn stars ionizes the surrounding gas, causing it to glow and illuminate the spiral structure. Studies of this phenomenon have provided astronomers with invaluable data on the interplay between star formation and galactic evolution. The cosmic dynamo of M51 has also been a laboratory for exploring the effects of galactic interaction. When the satellite galaxy, the irregular companion, NGC 5195, grazes the disk of the primary galaxy, it creates shock waves that ripple through the interstellar medium. These waves compress gas, inducing bursts of star formation while also leaving behind arcs of older stellar populations. Observations of these effects have confirmed theoretical predictions about the role of tidal forces in triggering star formation. In the heart of the interstellar whirlpool, the core region reveals a supermassive black hole cloaked in an accretion disk of superheated matter. The behavior of this black hole has been scrutinized using X-ray and radio telescopes, revealing its episodic bursts of high-energy radiation. These emissions, sometimes accompanied by relativistic jets, provide critical data for studying the behavior of matter under extreme gravitational conditions. By comparing the activity of this galactic nucleus with others across the universe, researchers refine models of black hole growth and galaxy central dynamics. The gravitational interaction of the starlight whirlpool system with its companion also plays a crucial role in redistributing angular momentum within the larger galaxy. This redistribution explains the tightly wound nature of its spiral arms, which differ from the looser structures seen in other spiral galaxies. Through detailed kinematic studies using spectroscopic data, astronomers have mapped the velocity patterns of stars and gas within the system, confirming the presence of density waves that sustain the spiral arm's distinct shape over time. The galactic tidal beauty, with its richly detailed arms, has been a source of inspiration for the study of dark matter. The rotational velocities of stars in the outer regions of the galaxy suggest the presence of a dark matter halo that extends well beyond the visible boundaries. This hidden mass exerts a gravitational influence that stabilizes the galaxy and maintains the integrity of its spiral arms. Observations of the whirlpool-like entity have significantly contributed to the broader understanding of how dark matter shapes galaxies across the cosmos. From the vivid colors of the grand spiral nexus, observed in optical and ultraviolet wavelengths, to the infrared glow of its dusty interstellar medium, every observation provides a piece of the cosmic puzzle. Astronomers have leveraged instruments such as the Hubble Space Telescope and the Very Large Array to capture high-resolution images and spectra of this galactic system. These datasets not only enhance our understanding of this particular galaxy but also serve as a comparative baseline for studying more distant systems that share similar characteristics. The stellar collision nexus remains a site of frequent supernova activity. These cataclysmic events, often occurring in the spiral arms, are observable as brief yet extraordinarily bright flashes. Each supernova provides a unique opportunity to study nucleosynthesis, the creation of heavy elements such as gold and uranium. By analyzing the light curves and spectral lines of these events, scientists unravel the complex processes that govern the life cycles of massive stars and their explosive deaths. The cosmic turbine of NGC 5194 exemplifies how interactions between galaxies fuel dynamic processes. The bridge of material linking the primary galaxy to its companion is a testament to the power of gravitational forces. This bridge, composed of stars, gas, and dust, allows for material exchange between the two galaxies, further complicating and enriching their evolution. Simulations of this interaction, conducted using advanced computational models, have allowed scientists to recreate the observed structures and dynamics, shedding light on similar processes occurring in other galactic systems. As our understanding of the intergalactic vortex deepens, it becomes increasingly clear that this galaxy is more than just a striking visual feature in the night sky. It is a cornerstone for scientific exploration, offering insights into a wide array of cosmic phenomena, from the formation of planetary systems to the large-scale structure of the universe. With each new discovery, the whirlpool system continues to remind us of the intricate and awe-inspiring nature of the cosmos. The celestial whirlpool pair, with its iconic sweeping arms and brilliant central hub, continues to unravel the mysteries of the universe. While its beauty has captivated stargazers for centuries, it is the depth of scientific data embedded in its structure that makes it invaluable to astrophysics. The primary galaxy, often described as the spiral dynamo of the north sky, acts as a natural laboratory for studying the forces that shape galaxies, drive star formation, and govern cosmic interactions. One of the key areas of research in this galactic wonder is the role of density waves in forming and maintaining its spiral arms. Unlike solid structures, these arms are composed of stars, gas, and dust moving in and out of gravitational traffic jams as they orbit the galactic center. These density waves compress gas clouds as they pass through, triggering waves of star formation. This self-sustaining process ensures that the whirlpool maintains its elegant spiral structure over millions of years. The ability to study this phenomenon so clearly in this system has helped astronomers understand how other grand design galaxies form and evolve. The intergalactic dance of NGC 5194 and its companion, NGC 5195, also reveals the long-term consequences of galactic mergers. Observational data shows that the smaller galaxy has already passed through the disk of the larger one multiple times, leaving behind tidal tails, arcs, and plumes of stars and gas. These remnants of gravitational interaction act as a memory of the encounter, offering a timeline of past collisions. Such detailed records are rare and provide critical evidence for understanding how galaxies like the Milky Way may have formed through similar interactions in the past. The heart of the cosmic vortex, the nucleus of NGC 5194, is not merely a quiet gathering of old stars. Instead, it is a bustling hub of activity dominated by the supermassive black hole at its center. With masses millions of times that of the Sun, this black hole exerts immense gravitational pull, drawing in surrounding gas and dust. As material spirals inward, it heats up to millions of degrees, releasing high-energy radiation that can be detected across vast cosmic distances. This phenomenon makes the nucleus of the whirlpool an active galactic nucleus, AGN, albeit less luminous than quasars. By studying AGNs like this one, scientists gain a better understanding of the relationship between black holes and their host galaxies. The Stellar Bridge Galaxy is also a treasure trove for studying the life cycle of stars. Its spiral arms host a variety of stellar populations, from bright blue giants in their infancy to red giants nearing the end of their lives. Using spectroscopy, astronomers can determine the chemical composition of these stars and their surrounding gas. This data reveals how generations of stars have enriched the galaxy with heavier elements, a process known as chemical evolution. These elements, forged in the cores of stars and released during supernovae, are the building blocks of planets, life, and even ourselves. Moreover, the whirlpool's proximity and clarity make it an ideal target for study between magnetic fields and star formation. The magnetic field lines, mapped using radio telescopes, align with the spiral arms, guiding the movement of charged particles and influencing the collapse of gas clouds into stars. Understanding these magnetic processes is crucial for piecing together the puzzle of star formation in galaxies across the universe. In recent years, the galactic gravitational showpiece has also become a focus for research into dark matter. The rotation curve of NGC 5194, which plots the orbital velocity of stars and gas at varying distances from the center, does not behave as expected based solely on visible matter. Instead, it suggests the presence of an unseen halo of dark matter that provides additional gravitational pull. This dark matter halo not only stabilizes the spiral structure but also plays a vital role in shaping the galaxy's overall dynamics. The whirlpool-like nexus has even contributed to the study of cosmic expansion. Using the Cepheid variable stars within its arms, astronomers have refined measurements of the Hubble constant, a key parameter that describes the rate at which the universe is expanding. By comparing these observations with those of other galaxies, researchers can test models of cosmology and explore mysteries such as dark energy. Beyond its scientific contributions, the cosmic tidal sculpture continues to inspire awe and wonder. Its breathtaking images, captured by observatories like Hubble, have been widely shared and studied, igniting public interest in astronomy and space exploration. Each image reveals new layers of complexity, from the intricate dust lanes that weave through its spiral arms to the faint tidal streams that hint at its tumultuous past. As telescopes become more advanced, the Whirlpool Galaxy and its companion will undoubtedly yield even more secrets. The upcoming generation of observatories, such as the James Webb Space Telescope, promises to peer deeper into the infrared, unveiling hidden star-forming regions and the faintest structures in the system. These discoveries will not only enhance our understanding of the Whirlpool Galaxy but also provide broader insights into the processes that govern the evolution of galaxies throughout the cosmos. The Whirlpool system, with its interplay of beauty, science, and cosmic history, stands as a symbol of humanity's quest to understand the universe. Each observation, whether of its spiral arms, its active nucleus, or its gravitational interactions, brings us closer to answering the fundamental questions about our origins and the nature of the cosmos itself. Should I continue delving into more aspects or refine specific sections further? The majestic spiral of Cain's Venatici remains a cornerstone in the study of galactic morphology, providing astronomers with unparalleled insights into the forces and processes that shape galaxies. Its ability to reveal complex, dynamic interactions, and a range of stellar phenomena has made it a focal point for both theoretical and observational research. The whirlpool, or stellar maelstrom, as it is sometimes called, serves as a gateway to understanding the broader mechanisms that govern cosmic evolution. One of the most striking aspects of the interstellar dynamo is the intricate balance between chaos and order. Despite the violent gravitational interactions with its companion, the spiral nexus has maintained its well-defined structure. This paradox is explained through the concept of density wave theory, where spiral arms are not static features but rather regions of higher density that move through the galaxy. This dynamic behavior allows the arms to persist even as individual stars and gas clouds move through them. The study of this mechanism has implications far beyond M51, helping astronomers decode the behavior of spiral galaxies across the universe. The galactic tidal duo offers a rare glimpse into the early stages of a galactic merger, a process that can take billions of years to complete. Simulations show that the smaller galaxy, often referred to as the stellar intruder, is gradually losing its distinct identity as it becomes inter-whirlpool. This ongoing interaction provides a live demonstration of how galaxies grow and evolve through accretion and mergers, processes that are thought to have played a major role in the formation of massive elliptical galaxies observed today. Another remarkable feature of the celestial whirlpool pair is the bridge of material connecting NGC 5194 and its companion. This stellar and gaseous bridge is a direct result of tidal forces, where the gravitational pull of the smaller galaxy distorts the disk of the larger one. The material within this bridge includes young stars, molecular gas, and interstellar dust, all of which are subjected to intense radiation and gravity. Detailed observations of this bridge have provided critical data on how tidal interactions redistribute material within and between galaxies, fueling star formation and triggering bursts of activity. The whirlpool, often referred to as also stands out as a prolific factory for stellar creation. Infrared observations reveal the presence of dense molecular clouds within its spiral arms, where conditions are ripe for the birth of new stars. These regions, often hidden in optical wavelengths by interstellar dust, are illuminated in the infrared spectrum, offering a clearer picture of the early stages of stellar formation. The ongoing starburst activity in the whirlpool is not just a localized phenomenon but a cosmic relay, as the energy and materials of stars will shape the future. The stellar whirlpool system is also a key site for studying the end stages of stellar evolution. The supernovae observed in its arms are not isolated events but rather the natural culmination of a star's life cycle. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse, releasing a tremendous amount of energy and ejecting heavy elements into the surrounding medium. Each supernova observed in M51 has provided unique data on the mechanisms of core collapse, the properties of neutron stars and black holes, and the enrichment of the interstellar medium. Beyond the stars, the whirlpool galaxy reveals the enigmatic role of dark matter in shaping cosmic structures. While the visible mass of the galaxy accounts for its luminous features, it cannot explain the observed rotational velocities of stars in its outer regions. This discrepancy points to the presence of a vast halo of dark matter, an invisible but critical component of the galaxy. By studying the rotational dynamics of M51, astronomers have refined models of dark matter distribution and its influence on galactic evolution. The galactic vortex of NGC 5194 also contributes to our understanding of feedback mechanisms in galaxies. The central black hole, through its accretion activity, generates powerful winds and jets that can influence star formation across the galaxy. This feedback loop, where the energy output of the nucleus regulates the availability of gas for star formation, is a key factor in determining the life cycle of galaxies. Observations of these processes in M51 have helped validate theories about the coevolution of supermassive black holes and their host galaxies. The whirlpool's companion, sometimes dubbed the stellar companion nexus, plays an equally vital role in shaping the primary galaxy. As it orbits and interacts with NGC 5194, it acts as both a disruptor and a catalyst. The gravitational forces exerted by the smaller galaxy create tidal streams and induce bursts of star formation, while also redistributing angular momentum within the system. This dynamic interplay offers a microcosm of the larger processes at work in galaxy clusters, where interactions between member galaxies drive the evolution of the entire system. On the observational front, the whirlpool-like entity has been a proving ground for cutting-edge technology. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have been used to study the cold molecular gas in the galaxy, providing a detailed map of the raw materials available for star formation. Meanwhile, the James Webb Space Telescope promises to unveil details about the galaxy's hidden regions, shedding light on its youngest stars and the earliest phases of stellar evolution. The celestial tidal marvel continues to captivate astronomers and the public alike. Its visual appeal, combined with its scientific significance, makes it a cornerstone of modern astrophysics. As our tools and techniques for exploring the cosmos improve, the Whirlpool Galaxy will undoubtedly remain a focal point for discovery, offering new insights into the nature of the universe and our place within it. The spiral marvel of Canes Venatici, often hailed as a galactic masterpiece, remains an enduring focus of cosmic exploration. Its prominent features and ongoing processes make it a living laboratory for unraveling universal mysteries, from the smallest scales of star formation to the vast influence of gravitational forces across millions of light-years. The Celestial Tidal Symphony, as it's also called, is not just a static image of the cosmos but a dynamic and evolving system. The gravitational interplay between the primary galaxy, NGC 5194, and its smaller satellite, NGC 5195, serves as a clear demonstration of how galaxies grow, interact, and transform over cosmic timescales. Current models suggest that the smaller galaxy has passed through the larger one's disk multiple times, leaving behind ripples of star formation, streams of displaced gas, and arcs of stellar populations. Each pass disrupts and reinvigorates the system, triggering phenomena that provide critical insights into galaxy formation and evolution. One of the most scientifically valuable aspects of the grand spiral dynamo is the interplay between its spiral arms and its interstellar medium. These arms are defined by their luminous regions of star formation, where gas clouds collapse under their own gravity to form stars. However, these regions are not evenly distributed, they are influenced by the density waves propagating through the galactic disk. The study of these waves has refined our understanding of how spiral structures are maintained in galaxies and how material is redistributed within them. The stellar collision pair has also become a key source for exploring the complex life cycle of galaxies. Tidal forces from the interaction with its companion have stripped stars and gas from the primary galaxy, creating tidal tails that arc far beyond its visible disk. These features are not only visually stunning but also contain vital information about the mass and composition of the interacting galaxies. Observations of these tidal streams have allowed astronomers to reconstruct the history of the interaction, providing a timeline for when and how the galaxies began their gravitational dance. The cosmic whirlpool engine, as some refer to it, is also a prolific site for stellar death and rebirth. Observations of supernovae within the galaxy's arms have offered invaluable data on the mechanisms of stellar explosions and their role in the cosmic cycle. These events release heavy elements like iron, nickel, and gold into the interstellar medium, enriching it and paving the way for the next generation of stars and planets. Each supernova leaves behind either a neutron star or a black hole, depending on the mass of the progenitor star, contributing to the population of compact objects within the galaxy. In addition to its stellar drama, the galactic nexus of NGC 5194 has become a focal point for studying the role of magnetic fields in shaping galaxies. Radio observations have revealed that magnetic field lines align with the galaxy's spiral arms, acting as invisible scaffolding that guides the movement of charged particles and influences star formation. These findings have implications for understanding the role of magnetism in other spiral galaxies and even in the early stages of galaxy formation in the universe. The whirlpool-like giant has also been instrumental in studying the enigmatic nature of dark matter. By analyzing the rotation curves of the galaxy, astronomers have determined that the visible matter within the galaxy cannot account for its observed gravitational effects. Instead, a massive halo of unseen dark matter surrounds the galaxy, exerting a stabilizing influence on its structure. This discovery has made the whirlpool a cornerstone in the ongoing quest to understand the true nature of dark matter and its role in the cosmos. The galactic stellar forge, as NGC 5194 is sometimes known, is equally valuable for its contributions to the study of cosmic feedback. The supermassive black hole at its core, surrounded by an accretion disk of infalling material, generates powerful outflows of energy. These outflows interact with the surrounding interstellar medium, heating and dispersing gas and regulating star formation within the galaxy. This process, known as feedback, is a critical component of galaxy evolution, and the whirlpool provides a rare opportunity to observe it in action. The interaction between the interstellar symphony and its companion has also reshaped the orbits of stars within the primary galaxy. As the smaller galaxy's gravity pulls on the whirlpool's disk, it creates complex patterns of motion that can be observed using spectroscopic techniques. These patterns offer a unique window into the dynamics of galactic disks and the long-term effects of tidal forces. By studying these motions, astronomers have gained a deeper understanding of how galaxies settle into equilibrium after collisions and mergers. The whirlpool system has also been a proving ground for some of the most advanced observational technologies. Instruments aboard the Hubble Space Telescope have provided high-resolution images that reveal the galaxy's intricate dust lanes, star clusters, and luminous core. Ground-based observatories equipped with adaptive optics have further enhanced our ability to study the galaxy, while radio telescopes like the Very Large Array have mapped the distribution of neutral hydrogen gas, shedding light on the large-scale structure of the system. Looking to the future, the Whirlpool Galaxy is poised to reveal even more secrets as new technologies come online. The James Webb Space Telescope, with its unparalleled infrared capabilities, will peer deep into the dust-shrouded regions of the galaxy, uncovering hidden star-forming regions and providing unprecedented detail on its youngest stars. Meanwhile, next-generation radio telescopes like the Square Kilometre Array will map the galaxy's magnetic fields and gas dynamics with unparalleled precision. The celestial maelstrom remains not only a testament to the beauty of the cosmos but also a key to understanding its underlying mechanics. Its intricate structure, dynamic interactions, and rich history make it a natural laboratory for exploring the fundamental principles of astrophysics. As our tools and techniques for studying the universe continue to evolve, the Whirlpool Galaxy will undoubtedly remain a centerpiece of scientific discovery, offering new insights into the nature of galaxies and their role in the grand tapestry of the universe. The dynamic spiral of Cain's Venatici, scientifically known as NGC 5194, continues to serve as a cornerstone for cutting-edge astrophysical research. Its wealth of observable phenomena has made it an unparalleled laboratory for investigating galaxy formation, stellar evolution, dark matter dynamics, and even the broader mechanisms governing cosmic structure. The data derived from the Whirlpool Galaxy system consistently refine our theoretical models and challenge existing paradigms in galactic astrophysics. One of the most studied aspects of this grand spiral dynamo is its remarkably well-defined spiral arms, which serve as a physical manifestation of density wave theory. Proposed in the mid-20th century, this theory suggests that spiral arms are not fixed structures but rather areas of increased density that move like waves through the galaxy's disk. In this model, stars, gas, and dust flow in and out of the spiral arms, much like cars slowing down and speeding up in a traffic jam. The arms of the galactic whirlpool nexus are active zones of star formation. As the density waves compress interstellar gas clouds, the increased pressure triggers the collapse of these clouds, leading to the birth of new stars. This process is observable in the bright knots of young, massive stars within the arms, which emit intense ultraviolet radiation and ionize surrounding hydrogen gas. These regions, often referred to as H2 regions, glow brightly in optical wavelengths and are key markers of ongoing star formation. Using spectroscopic data from instruments like the Sloan Digital Sky Survey, SDSS, and the Multi-Unit Spectroscopic Explorer, MUSE, astronomers have mapped the velocity fields within these arms. These studies reveal the intricate interplay between gas dynamics, star formation, and feedback from massive stars. The high-resolution data also highlight the role of turbulence and magnetic fields in shaping the star-forming regions, providing new insights into the physical conditions that drive stellar birth in spiral galaxies. The cosmic tidal pair, consisting of NGC 5194 and its companion NGC 5195, exemplifies the dramatic effects of gravitational interactions between galaxies. These tidal forces are responsible for many of the features observed in the Whirlpool galaxy, including its sharp spiral arms and extended tidal tails. The gravitational interaction between the two galaxies has also induced large-scale gas flows within NGC 5194, redistributing material and fueling bursts of star formation. One of the most striking results of this interaction is the creation of a luminous bridge of stars and gas that connects the two galaxies. This structure is a direct consequence of tidal stripping, where gravitational forces from the smaller galaxy pull material from the larger one. Observations of this bridge in multiple wavelengths, including radio, optical, and infrared, have provided critical data on the dynamics of tidal interactions and the role of these processes in galaxy evolution. Hydrodynamic simulations of the stellar collision duo have allowed researchers to reconstruct the history of their interaction. These models suggest that NGC 5195 has passed through the disk of NGC 5194 at least once, with each encounter generating new waves of star formation and reshaping the structure of both galaxies. Such simulations are not only crucial for understanding the specific history of the Whirlpool galaxy but also serve as a template for studying similar interactions in other systems. At the core of the interstellar vortex, a supermassive black hole with a mass estimated to be millions of times that of the Sun dominates the dynamics of the central region. This black hole, surrounded by an accretion disk of infalling material, occasionally flares in bursts of high-energy radiation. These emissions, observed in X-ray and radio wavelengths, classify the nucleus as a low-luminosity active galactic nucleus, AGN. The AGN in NGC 5194 provides a unique opportunity to study the feedback mechanisms that regulate galaxy evolution. As the black hole accretes material, it releases powerful jets and winds that interact with the surrounding interstellar medium. These outflows can heat and disperse gas, suppressing star formation in the central regions of the galaxy. This process, known as AGN feedback, is a key component of galaxy evolution models and helps explain the observed relationships between black hole mass and the properties of their host galaxies. Recent observations using the Chandra X-ray Observatory have revealed intricate structures in the hot gas surrounding the nucleus. These structures, including shock fronts and cavities, are thought to be the result of interactions between the AGN outflows and the surrounding interstellar medium. By studying these features, astronomers are gaining new insights into the role of black holes in shaping their host galaxies. The galactic dynamo nexus is also a prime site for investigating the role of magnetic fields in shaping galactic structure and star formation. Using radio observations, astronomers have mapped the magnetic field lines within the galaxy, which closely follow the spiral arms. These fields play a crucial role in regulating the collapse of gas clouds, influencing both the rate and efficiency of star formation. The alignment of magnetic fields with the spiral arms is thought to result from the interaction between density waves and the galaxy's differential rotation. This process, known as the alpha-omega dynamo, amplifies and organizes the magnetic fields, creating the ordered patterns observed in the Whirlpool galaxy. The study of these fields not only enhances our understanding of M51 but also provides broader insights into the role of magnetism in other galaxies. The rotation curve of the stellar Whirlpool system provides compelling evidence for the existence of dark matter. Observations show that the orbital velocities of stars in the outer regions of the galaxy remain constant, rather than decreasing as would be expected based on the visible mass alone. This discrepancy suggests the presence of a massive dark matter halo that extends far beyond the visible boundaries of the galaxy. By combining optical and radio observations, astronomers have mapped the distribution of dark matter within the Whirlpool galaxy. These studies have refined our understanding of the role of dark matter in shaping the structure and dynamics of galaxies. They also contribute to the broader effort to understand the nature of dark matter, one of the most profound mysteries in modern physics. The luminous spiral pair serves as a microcosm of the processes that drive cosmic evolution. Its well-documented history of interaction, active star formation, and dynamic feedback mechanisms provides a detailed case study for understanding how galaxies grow and change over time. By comparing the Whirlpool galaxy to more distant systems, astronomers can trace the evolutionary pathways of galaxies across cosmic history, from their formation in the early universe to their present-day structures. As observational technology continues to advance, the Whirlpool-like entity will undoubtedly yield even more secrets. Instruments like the James Webb Space Telescope and next-generation radio arrays promise to provide unprecedented detail on its hidden regions, offering new insights into the processes that drive galaxy evolution. Each discovery brings us closer to answering the fundamental questions about the nature of the universe and our place within it. The spiral marvel of the northern skies, a system defined by its vivid, intricate design and profound scientific depth, is a living chronicle of the cosmos, waiting to unveil its secrets to those who study it. Beyond its captivating appearance lies an extraordinary network of physical phenomena and cosmic forces that challenge and refine humanity's understanding of the universe at every level. This stellar system, often romantically described as a cosmic hurricane frozen in time, is more than a grand visual masterpiece. It is a dynamic interaction of gravity, magnetism, and matter, creating a stage where the rules of galactic evolution play out vividly. Every spiral arm, star-forming region, and shock wave in this system is a vital clue to the nature of galaxy formation and the interconnected forces shaping the fabric of the universe. The gravitational bond between the luminous whirlpool nexus and its satellite galaxy, often called the cosmic intruder, is a phenomenon both violent and beautiful. Their interaction creates gravitational tidal forces so immense that they physically distort the disks of both galaxies, producing long tidal tails and streams of gas that stretch across tens of thousands of light-years. These streams, glowing faintly in infrared light, are thought to carry the raw ingredients for star formation, acting as highways of interstellar matter connecting the two galaxies. The spiral arms of the interstellar dynamo, with their exquisite definition, are sculpted not by chance but by the collision and compression of gas clouds triggered by these tidal forces. The density waves moving through the disk act as catalysts, creating the conditions necessary for massive star formation. These stars, though young and short-lived, release copious amounts of energy and radiation, which then propagate outward, lighting up the spiral arms in ultraviolet and optical wavelengths. This cycle of compression, star formation, and feedback defines the very heartbeat of the galaxy. Recent studies have revealed that these arms are rich not only in stars but also in enigmatic structures such as molecular gas clouds and filaments of interstellar dust. Observations from the Atacama Large Millimeter/Submillimeter Array, ALMA, have identified regions within the arms that are on the verge of collapse, giving astronomers a chance to witness the earliest stages of stellar birth. These discoveries have expanded humanity's understanding of how gas turns into stars, providing critical insights into one of the most fundamental processes in the cosmos. But the galactic whirlpool pair holds mysteries that go far beyond star formation. Deep within its luminous core lies an engine of incomprehensible power, a supermassive black hole. This behemoth, millions of times the mass of the Sun, exerts a gravitational influence so strong that it shapes the very dynamics of the galaxy. Material falling into this black hole forms an accretion disk, which heats to millions of degrees, producing powerful jets and outbursts of radiation that can be detected across the electromagnetic spectrum. These emissions are not merely fascinating, they are clues to the physics of matter under extreme gravitational forces, revealing processes that cannot be replicated on Earth. The role of the black hole extends beyond its immediate vicinity. Its energy outbursts send shockwaves through the interstellar medium, heating gas clouds and disrupting their collapse into stars. This dual role of creation and destruction makes the nucleus of the whirlpool entity a focal point for understanding the delicate balance of forces that governs galaxy evolution. By observing this system, scientists are piecing together how black holes influence not only their host galaxies but also the broader cosmic environment. One of the most intriguing features of the cosmic tidal symphony is the faint, ghostly glow of its dark matter halo. This invisible structure, which outweighs the visible galaxy by several times, is inferred from the motion of stars in the galaxy's outer regions. The rotational velocity of these stars defies the expectations set by visible matter alone, suggesting the presence of a vast, unseen mass. This discovery is not unique to the whirlpool but is a hallmark of nearly all galaxies, making it a cornerstone of modern astrophysics and a gateway to understanding the elusive nature of dark matter. While much of the galaxy's activity is focused on its dense core and active arms, its outer regions tell a quieter but equally compelling story. Here, in the faint periphery of the luminous spiral nexus, ancient stars orbit in near isolation, remnants of an earlier epoch in the galaxy's history. These stars, some of which are globular clusters, serve as living fossils, preserving the chemical signatures of the galaxy's past. By analyzing their light, astronomers can reconstruct the formation history of the galaxy, tracing its evolution back billions of years. The ongoing interaction with the smaller satellite galaxy continues to shape the destiny of this celestial pair. Simulations suggest that the two galaxies are locked in a gravitational embrace that will eventually culminate in their merger, a process that could take hundreds of millions of years. This merger will not be a simple union but a chaotic and transformative event, likely resulting in the formation of an entirely new galaxy type. The tidal forces unleashed during this collision will scatter stars, gas, and dust, while triggering waves of star formation and reshaping the system's structure in ways that are only beginning to be understood. Adding to the intrigue, the grand stellar whirlpool has proven to be a prolific site for supernovae. These stellar explosions, among the most energetic events in the universe, are a natural consequence of the galaxy's intense star formation. Each supernova not only marks the death of a massive star but also enriches the surrounding medium with heavy elements, creating the building blocks for future generations of stars and planets. Observing these events in real time has allowed scientists to refine their models of stellar death and the mechanics of core-collapse supernovae. The more scientists delve into the depths of the galactic maelstrom, the more questions arise. How do its magnetic fields interact with the spiral arms? What role does turbulence in its interstellar medium play in regulating star formation? And how will its eventual merger with its companion reshape its future? These questions drive a relentless pursuit of knowledge, pushing the boundaries of what humanity knows about the universe. As humanity's observational tools grow ever more sophisticated, from the James Webb Space Telescope to ground-based observatories with adaptive optics, the dynamic Vortex galaxy will undoubtedly continue to yield its secrets. Each new discovery not only deepens our understanding of this iconic system but also provides a broader context for understanding the universe as a whole. The Whirlpool Galaxy is not just a spectacle, it is a living narrative of cosmic forces, a story of birth, transformation, and eventual rebirth on a scale that defies imagination. And in its glowing arms and luminous core lies the promise of countless more revelations to come. The cosmic maelstrom, as astronomers have come to know it, is far more than a galactic archetype, it is a symphony of forces, an interplay of energy and gravity that operates on a stage so vast that its full drama unfolds over tens of millions of years. Every photon escaping its vibrant spiral arms carries with it the whispers of physical processes that have shaped the universe for billions of years. This intricate galactic tapestry serves as both a map and a mirror, reflecting the universal laws of nature. At the heart of this stellar whirlpool, the supermassive black hole acts as both creator and destroyer. Its influence extends far beyond the core, shaping not just the dynamics of nearby stars but also regulating star formation across the galaxy. When gas spirals into the black hole's accretion disk, it heats up to extraordinary temperatures, emitting intense X-rays and sometimes forming powerful relativistic jets. These jets, moving at nearly the speed of light, can punch through the galaxy's interstellar medium, creating shockwaves that compress gas clouds or, conversely, blow them apart. This mechanism, known as feedback, is a key process in regulating galaxy evolution, and the whirlpool's active nucleus is a pristine laboratory for studying it. Observations in the X-ray spectrum using instruments like Chandra have revealed fascinating details about this activity. Hot gas in the nucleus of the interstellar vortex glows in X-rays, outlining the regions where energy from the black hole is interacting with its surroundings. These high-energy interactions are not limited to the nucleus alone. Fainter X-ray emissions trace supernova remnants scattered throughout the spiral arms, powerful evidence of the galaxy's prolific star formation and the violent deaths of massive stars. These remnants also emit neutrinos and cosmic rays, whose detection on Earth provides a direct link between this galaxy and our own. The luminous dynamo also showcases an abundance of molecular gas, the raw material for star formation. Using radio telescopes like ALMA, scientists have mapped vast reservoirs of cold molecular hydrogen in its arms. These cold, dense regions are peppered with massive, turbulent gas clouds that are collapsing to form stars. Within these clouds, gravitational instabilities trigger the formation of stellar clusters, which then light up the arms in ultraviolet and visible wavelengths. But the process is not straightforward. The interplay between gravity, turbulence, magnetic fields, and radiation pressure creates a complex environment where only a fraction of the gas forms stars. Magnetic fields, which have been mapped using polarized radio waves, thread through the spiral tidal nexus, acting as both an inhibitor and a guide for gas flows. These fields channel charged particles along their lines, influencing the motion of gas and dust and shaping the birthplaces of stars. The alignment of magnetic fields with the galaxy's spiral arms is a striking example of the cosmic order arising from seemingly chaotic processes. As if the dynamism of its spiral arms weren't enough, the galactic tidal symphony reveals yet another layer of intrigue: the presence of interstellar shocks caused by the passage of its satellite galaxy, NGC 5195. When this smaller galaxy passed through the disk of the whirlpool, it induced massive waves of compression, heating gas clouds and triggering bursts of star formation. These shock fronts are visible as arcs of ionized gas glowing in H-alpha light, a testament to the ongoing impact of this gravitational interplay. These waves of activity are rippling outward, reshaping the structure and composition of the galaxy's outer disk. The gravitational interaction has also created the iconic bridge of material that connects the whirlpool system to its smaller companion. This bridge, made of stars and interstellar gas, is a physical testament to the power of tidal forces. Spectroscopic studies of the bridge reveal peculiar velocity profiles, with gas moving in highly complex patterns. These measurements confirm that material is actively being transferred between the two galaxies, fueling star formation in both systems and altering their evolutionary trajectories. In addition to being a stellar nursery, the celestial maelstrom is a galactic forge where heavier elements are produced and dispersed. Every massive star that forms in the spiral arms eventually ends its life in a spectacular supernova, releasing elements such as carbon, oxygen, and iron into the surrounding medium. These enriched gas clouds later coalesce into new stars and planets, embedding the fingerprints of previous generations into future ones. The whirlpool galaxy is, in essence, a self-sustaining cosmic engine, perpetually recycling and renewing itself. Dark matter plays a pivotal role in maintaining this engine. The rotational curve of the spiral vortex defies classical Newtonian expectations, with stars at the outer edges moving much faster than predicted by the visible mass alone. This discrepancy is attributed to a massive halo of dark matter that envelopes the galaxy, extending well beyond its visible edge. The presence of this unseen mass not only stabilizes the spiral structure but also influences the dynamics of tidal interactions with its companion galaxy. By studying the distribution and influence of dark matter in the whirlpool galaxy, astronomers are refining their understanding of this mysterious component of the universe, which constitutes nearly 27% mass energy content. The stellar collision nexus also serves as a laboratory for studying cosmic dust, an often overlooked but critical component of the interstellar medium. Dust grains, composed of silicates, carbon, and other heavy elements, are formed in the atmospheres of dying stars and during supernova explosions. These tiny particles absorb and scatter light, making them both a challenge and a boon for observational astronomy. In the whirlpool, dust lanes weave through the spiral arms, casting shadows and creating stark contrasts that highlight the galaxy's structure. Infrared observations from the Spitzer Space Telescope and the James Webb Space Telescope have illuminated these dust-rich regions, revealing the hidden star-forming factories buried within. On the largest scales, the dynamic spiral entity interacts not only with its companion but also with the surrounding intergalactic medium. Faint, diffuse emissions of gas have been detected beyond its visible disk, hinting at interactions with the larger cosmic web of matter that connects galaxies across vast distances. These faint emissions, traced through neutral hydrogen studies, reveal that the Whirlpool galaxy is not an isolated system but part of a much larger, interconnected structure. Cosmic web is the scaffolding of the universe, and the Whirlpool gives a glimpse into how galaxies draw material from these intergalactic reservoirs. As research continues, the Whirlpool-like giant serves as a beacon of discovery, challenging astronomers to push the boundaries of technology and theory. It is a system that operates on timescales so vast and scales so immense that it humbles the human imagination. Yet, within its swirling arms and luminous core, it carries the answers to some of the most profound questions about the nature of the cosmos and our place within it. Every photon, every gas, every burst of energy from a dying star adds to the story of a galaxy that is as much a laboratory as it is a masterpiece of the universe. Let me know if you'd like me to further expand specific sections or explore additional cosmic phenomena. The spiral masterpiece of Cain's Venatici, often heralded as one of the most studied galactic systems in our cosmic neighborhood, continues to reveal mysteries that push the boundaries of astrophysics. Its dynamic environment, driven by an intricate interplay of gravity, radiation, magnetism, and dark matter, offers an unparalleled opportunity to study phenomena that are otherwise impossible to replicate on Earth. At the forefront of modern research lies the question of galactic interaction dynamics. The Whirlpool Galaxy, or Interstellar Collision Laboratory, has become a key observational target for understanding how galaxies evolve through interactions. The ongoing gravitational tug-of-war between NGC 5194 and its smaller companion, NGC 5195, serves as a natural experiment, offering astronomers a snapshot of a process that unfolds over hundreds of millions of years. Advanced hydrodynamic simulations have been employed to model the tidal forces sculpting the Whirlpool Galaxy's spiral arms and the extended gas bridges connecting the two galaxies. These simulations, powered by some of the world's most sophisticated supercomputers, reveal how repeated passes of NGC 5195 through the disk of NGC 5194 induce waves of star formation and redistribute mass across the system. Each pass acts like a stone dropped in a cosmic pond, generating ripples of compression that propagate outward through the galactic disk. These ripples trigger starbursts, intense periods of star formation that light up the galaxy in ultraviolet and infrared wavelengths. The galactic forge has become an essential focus for understanding these starbursts. Observations using the Hubble Space Telescope and the James Webb Space Telescope have identified compact clusters of young stars nestled within the spiral arms. These clusters are often surrounded by cocoons of ionized gas, glowing brightly in H-alpha light. By studying these regions, researchers have uncovered the role of turbulence in regulating star formation. Turbulence, driven by gravitational interactions, creates pockets of high-density gas within the arms, which collapse under their own gravity to form stars. The ongoing interaction has also exposed a remarkable phenomenon known as shock-induced star formation. As the companion galaxy passes through the whirlpool's disk, it generates shock fronts, regions where gas is compressed and heated by the collision of massive interstellar flows. These shock fronts, observed in the far-infrared and millimeter wavelengths, are prolific sites for star formation. The conditions within these regions are so extreme that they provide a glimpse into the processes that likely occurred during the universe's early epochs when galaxy collisions were more frequent. The cosmic dynamo also offers a rare opportunity to study the role of magnetic fields in shaping galactic structure. Using advanced radio telescopes like the Very Large Array and the Square Kilometre Array, SKA, astronomers have mapped the magnetic field lines threading through the galaxy's spiral arms. These fields, amplified by the galaxy's rotation and density waves, guide the movement of charged particles and influence the dynamics of interstellar gas. Magnetic fields are thought to play a critical role in the collapse of molecular clouds, acting as both a brake and a catalyst for star formation. Adding another layer of complexity, the stellar collision symphony is an active participant in the cosmic cycle of matter and energy. Its spiral arms are rich in dust and molecular gas, the raw materials for star formation, but they are also constantly being replenished by the deaths of massive stars. Supernovae, which occur frequently in this starbursting galaxy, release heavy elements into the interstellar medium, enriching it with the building blocks for planets, life, and future generations of stars. Each supernova is a localized explosion of energy, creating shockwaves that ripple through the surrounding medium, compressing gas and seeding the next wave of star formation. The study of supernova remnants in the whirlpool has become a critical area of astrophysical research. Instruments like Chandra and XMM Newton have detected the faint X-ray glow of hot gas in these remnants, providing a window into the late stages of stellar evolution. These observations are complemented by neutrino detections on Earth, which offer a rare glimpse into the processes occurring in the cores of dying stars. The Whirlpool Galaxy has thus become a key player in the global effort to understand core collapse supernovae, which are among the most powerful events in the universe. The gravitational tidal theater also serves as a testing ground for theories of dark matter distribution. By analyzing the motions of stars and gas in the galaxy's outer regions, astronomers have reconstructed the shape and extent of its dark matter halo. These studies reveal that the dark matter in NGC 5194 forms an enormous, invisible halo that extends far beyond the visible disk, encompassing both the primary galaxy and its satellite. This halo not only stabilizes the spiral arms but also influences the dynamics of the interaction with NGC 5195. By comparing these findings to simulations of galaxy formation, researchers are refining their understanding of how dark matter drives the growth and evolution of galaxies. On the larger scale, the luminous whirlpool nexus offers insights into the role of galaxies within the cosmic web, the vast network of dark matter and gas that connects galaxies across the universe. Neutral hydrogen observations using radio telescopes have revealed faint streams of gas extending from the whirlpool into the intergalactic medium, hinting at ongoing interactions with the larger cosmic environment. These gas streams may represent the inflow of material from the cosmic web into the galaxy, providing the fuel for future star formation. Perhaps one of the most tantalizing mysteries of the dynamic spiral entity is its eventual fate. The interaction with NGC 5195 is a prelude to an inevitable merger, a process that will transform the Whirlpool galaxy into an entirely new structure. Simulations predict that this merger will destroy the elegant spiral pattern, replacing it with a chaotic mix of stars and gas. Over time, the system will settle into a more stable elliptical or lenticular form. While this transformation will take hundreds of millions of years to complete, it offers a glimpse into the ultimate destiny of many spiral galaxies, including our own Milky Way, which is on a collision course with the Andromeda Galaxy. As telescopes grow ever more powerful and theoretical models become increasingly sophisticated, the stellar tidal giant will undoubtedly continue to yield new discoveries. Its dynamic environment, rich in observable phenomena, makes it a cornerstone of modern astrophysics and a symbol of the beauty and complexity of the cosmos. Each new revelation from the Whirlpool galaxy brings humanity one step closer to unraveling the ultimate mysteries of the universe, reminding us that, even in the vastness of space, the laws of physics remain beautifully consistent and endlessly fascinating. Let me know if you'd like me to go deeper into specific aspects or expand further on recent research. The luminous spiral forge, a stellar laboratory unlike any other, continues to intrigue scientists with its dynamic processes and relentless activity. Its seemingly tranquil beauty hides a cauldron of physical forces that drive the evolution of galaxies, create and destroy stars, and sculpt the universe on both local and cosmic scales. Every new observation of this celestial masterpiece peels back another layer of its complexity, offering deeper insights into phenomena that have shaped the cosmos for billions of years. One of the most compelling ongoing investigations into the interstellar vortex focuses on its remarkable ability to sustain starburst activity over extended periods. While star formation is common in spiral galaxies, the Whirlpool is unique in its high efficiency at converting gas into stars, particularly in the dense regions of its spiral arms. Detailed spectroscopic studies have revealed the chemical composition of these regions, showing an abundance of heavier elements, products of countless previous generations of stars. This enrichment accelerates the process of star formation by cooling the gas more efficiently, allowing it to collapse into stars at a faster rate. What sets the cosmic dynamo apart is the extraordinary diversity of stellar populations within it. The galaxy's arms are home to massive, hot, young stars that shine brightly in ultraviolet light, while its outskirts harbor older, cooler stars that trace the galaxy's ancient history. This juxtaposition allows astronomers to study the full spectrum of stellar evolution in a single system. By comparing the properties of these different populations, researchers can reconstruct the history of star formation in the galaxy and understand how its interactions with NGC 5195 have influenced its development. The tidal collision duo also serves as a natural laboratory for investigating the behavior of interstellar dust, an essential but often overlooked component of galaxies. Dust grains, though tiny, play a critical role in the life cycle of stars and planets. They absorb ultraviolet and visible light, re-emitting it as infrared radiation, which has been captured in exquisite detail by the Spitzer Space Telescope and, more recently, the James Webb Space Telescope. These observations reveal intricate patterns of dust lanes weaving through the spiral arms, often outlining regions of intense star formation. The dust also provides the raw material for the formation of planets, making the Whirlpool a key system for understanding the origins of planetary systems like our own. A particularly exciting avenue of research in the dynamic spiral nexus involves the study of stellar feedback mechanisms. Massive stars, while short-lived, profoundly influence their surroundings through intense radiation, stellar, and eventual supernova explosions. This feedback injects energy into the interstellar medium, creating shockwaves that compress gas clouds and trigger new waves of star formation. However, it can also have the opposite effect, dispersing gas and quenching star formation in certain regions. Understanding this delicate balance is crucial for unraveling the processes that govern galaxy evolution, and the whirlpool provides a vivid example of how these mechanisms play out in real time. Meanwhile, the Galactic Gravitational Laboratory continues to illuminate the enigmatic nature of dark matter, which is thought to make up the vast majority of the galaxy's mass. The rotational velocities of stars in the whirlpool's outer regions remain constant, defying the predictions of Newtonian physics based solely on visible matter. This discrepancy points to the presence of an extensive dark matter halo that stabilizes the galaxy's structure and drives its interactions with its companion. By studying the distribution of dark matter in this system, astronomers are gaining critical insights into its role in shaping the large-scale structure of the universe. The celestial whirlpool theater is also a prime target for investigations into galactic magnetic fields, which are notoriously difficult to study but are increasingly recognized as fundamental to the evolution of galaxies. The magnetic fields in the whirlpool, mapped using polarized radio observations, show a remarkable alignment with its spiral arms. These fields are thought to amplify and organize themselves through the galaxy's rotation and density wave patterns. They influence the motion of charged particles, guide the flow of gas, and even affect the collapse of molecular clouds into stars. The study of these fields in the whirlpool has opened a new frontier in astrophysics, linking small-scale processes like star formation to the large-scale dynamics of galaxies. The tidal bridge system connecting NGC 5194 and NGC 5195 is another area of intense study. This luminous structure, composed of stars, gas, and dust, is a direct result of the gravitational interaction between the two galaxies. Detailed spectroscopic analysis has revealed the velocities of gas within the bridge, showing complex motions that reflect the tidal forces at work. These interactions are not merely destructive, they also create opportunities for new star formation. The bridge itself contains regions of active star formation, illuminated by clusters of young, massive stars that have recently formed from the compressed gas. At the heart of the stellar whirlpool nexus, the supermassive black hole has profound influence on its surroundings. Recent observations using high-resolution X-ray and infrared telescopes have revealed that this black hole is relatively quiet compared to those in more active galaxies. However, periodic flares from its accretion disk suggest that it occasionally accretes material, releasing bursts of energy that ripple through the central region of the galaxy. These flares offer a rare opportunity to study the physics of accretion and the behavior of matter under extreme gravitational forces. The eventual fate of the spiral collision duo is a question that continues to captivate astronomers. Simulations predict that the ongoing interaction between NGC 5194 and NGC 5195 will ultimately lead to their merger, transforming the elegant spiral structure of the whirlpool into a chaotic elliptical or lenticular galaxy. This transformation will not be a quiet process, it will be marked by intense bursts of star formation, the redistribution of stars and gas, and the possible ejection of material into intergalactic space. Understanding this process is not only key to the future of the whirlpool but also to the broader question of how galaxies evolve over cosmic timescales. The dynamic intergalactic giant is more than just a single system, it is a window into the universe itself. Its intricate structures, dynamic processes, and rich history make it a microcosm of the forces that shape galaxies across the cosmos. As observational technology advances, from next-generation radio arrays to powerful space telescopes, the whirlpool will continue to reveal its secrets, challenging and expanding humanity's understanding of the universe. If you'd like, I can delve even deeper in discoveries or explore related topics further. The Grand Celestial Whirlpool, as it has often been called, continues to astonish astronomers with its intricate balance of chaos and order, offering a profound glimpse into the forces that sculpt galaxies. This cosmic tapestry is more than a visual marvel, it is a nexus of astrophysical phenomena, each one shedding light on the fundamental mechanics of the universe. Recent advances in multi-wavelength astronomy have opened new doors for studying the dynamic processes within this galactic masterpiece. Observations in radio, optical, infrared, and X-ray spectra have revealed the full spectrum of activity, from the cool molecular gas fueling star formation to the high-energy events near its core. By combining these datasets, researchers have constructed a comprehensive, multi-layered view of the interstellar tidal laboratory, uncovering details that were once beyond reach. A key area of exploration is the cold molecular gas within the whirlpool's spiral, the essential building blocks of star formation. Using ALMA, astronomers have mapped the distribution and kinematics of carbon monoxide, CO, a tracer molecule that reveals the presence of vast molecular clouds. These clouds, containing hydrogen gas too cold to detect directly, are the nurseries where stars are born. Intriguingly, the observations show that the molecular gas is not evenly distributed but instead concentrated in dense filaments aligned with the spiral arms. These filaments, shaped by the galaxy's density waves and magnetic fields, act as conduits funneling gas into regions of active star formation. In some areas, the turbulence within these molecular clouds is so intense that it creates localized pockets of extreme density, triggering the collapse of gas into stars at rates much higher than average. This phenomenon, often referred to as turbulence-driven star formation, has been observed in several regions of the whirlpool and has become a focal point for understanding how gravitational instabilities interact with turbulence to produce new stellar populations. These findings are vital for refining theoretical models of star formation, especially in galaxies experiencing tidal interactions. The dynamic spiral dynamo is also a treasure trove for studying the feedback effects of massive stars on their environments. In regions where young, massive stars have recently formed, their intense ultraviolet radiation ionizes the surrounding hydrogen gas, creating expansive H2 regions. These regions, visible in optical wavelengths as glowing clouds, are not only sites of active star formation but also the seeds of future stellar generations. However, the energy released by these stars also drives powerful stellar winds and supernovae, which inject energy back into the interstellar medium. This feedback can compress nearby gas, sparking new star formation, or disperse it, halting the process. The interplay between these competing effects is a key driver of the galactic star formation cycle and is vividly illustrated in the whirlpool's arms. Further in, closer to the core of the galactic tidal nexus, lies one of the most enigmatic components of the system, its supermassive black hole. Despite being relatively dormant compared to those in active galaxies, the whirlpool's black hole occasionally flares as it accretes material from its surroundings. These accretion events, observed in X-ray and infrared wavelengths, are brief but powerful, releasing immense energy that radiates outward through the galaxy. Such events offer a rare opportunity to study the behavior of matter in the extreme gravitational environment near a black hole, including the physics of relativistic jets and accretion disk dynamics. The role of magnetic fields in shaping the whirlpool structure is another area of cutting-edge research. Polarimetric observations have revealed that the magnetic field lines in the galaxy are closely aligned with its spiral, a feature that is thought to arise from the interaction between the galaxy's rotation and its density waves. These fields influence the motion of charged particles and the collapse of gas clouds, playing a critical role in the formation and evolution of stars. The ability to map these fields in such detail has provided a new dimension to our understanding of galactic dynamics, linking large-scale processes star formation. Between the spiral Titan and its satellite galaxy, NGC 5195, is a phenomenon of profound significance. The tidal forces generated by this interaction have not only shaped the whirlpool's spiral arms but also created a luminous bridge of material connecting the two galaxies. This bridge, composed of stars, gas, and dust, is a physical record of their gravitational encounter, offering a snapshot of a process that has shaped throughout the universe's history. Spectroscopic studies of the bridge have revealed complex motions, with gas moving at different velocities along its length. These findings suggest that the bridge is not merely a static structure but a dynamic region is actively being exchanged between the two galaxies. One of the most intriguing aspects of the stellar whirlpool nexus is its connection to the larger cosmic web, the vast network of dark matter and gas that permeates the universe. Observations of neutral hydrogen gas using radio telescopes have revealed faint streams of material extending from the whirlpool into intergalactic space. These streams are thought to represent the inflow of gas from the cosmic web into the galaxy, providing the fuel for future star formation. This discovery has profound implications for understanding how galaxies acquire the material they need to grow and evolve, particularly in the context of hierarchical galaxy formation. Another fascinating phenomenon in the dynamic interstellar forge is the role of dark matter in shaping its structure and dynamics. The rotational velocities of stars and gas in the galaxy's outer regions deviate significantly from what would be expected based on visible matter alone. This discrepancy is explained by the presence of a massive dark matter halo that extends far beyond the visible boundaries of the galaxy. By studying the distribution and influence of this halo, astronomers are gaining critical insights into the nature of dark matter, one of the most elusive components of the universe. The future of the grand galactic vortex is equally captivating. Simulations suggest that the ongoing interaction with NGC 5195 will eventually lead to a merger, transforming the whirlpool from a grand spiral into a more chaotic and diffuse structure. This merger, while destructive in some respects, will also create new opportunities for star formation as gas clouds are compressed and mixed during the process. Understanding this transformation is not only key to the future of the whirlpool but also to the broader question of how galaxies evolve over billions of years. As telescopes like the James Webb Space Telescope and next-generation observatories come online, the luminous spiral nexus will undoubtedly yield even more secrets. Its rich tapestry of phenomena, from star formation and supernovae to black holes and magnetic fields, makes it an unparalleled resource for exploring the universe's most profound mysteries. Each new discovery adds another layer to our understanding, reminding us that the cosmos is far more complex, interconnected, and awe-inspiring than we could ever imagine. Let me know if you'd like even more depth or exploration into specific phenomena. As we draw closer to the boundaries of what is known about the cosmic whirlpool, one truth remains clear: this galaxy is more than a celestial wonder, it is a testament to the intricate, interconnected forces that govern the universe. From the glowing star nurseries in its spiral arms to the ancient stars in its outskirts, from the bursts of energy unleashed by dying stars to the quiet but immense influence of its dark matter halo, the Whirlpool Galaxy stands as a microcosm of cosmic evolution. The story of the dynamic spiral nexus is still being written, one photon, one data set, one discovery at a time. It reminds us that galaxies, like life itself, are not static but dynamic, ever-changing, and deeply interconnected with the cosmos around them. Its gravitational dance with its companion galaxy will one day culminate in a merger that will transform both systems, creating a new, unique structure that will continue the cycle of creation and destruction on a cosmic scale. With every new observation and technological advancement, the interstellar dynamo teaches us more about the fundamental workings of the universe. It inspires scientists and stargazers alike to continue asking questions, to look deeper, and to reach farther into the vast expanse of space. The Whirlpool Galaxy, with its swirling arms and luminous core, will remain a beacon of discovery for generations to come, a reminder that the cosmos, though immense and unfathomable, is within our grasp to explore and understand. As humanity continues to push the boundaries of knowledge, the luminous whirlpool giant will stand as a symbol of what is possible when curiosity and innovation come together. Its mysteries will continue to unfold, challenging us to think bigger, dream further, and embrace the infinite possibilities of the universe. In its glowing arms and timeless beauty lies the promise of discovery, a promise that fuels our collective journey into the stars. In the silent vastness of the cosmos, an angel moves through the dark. Its wings stretch farther than light can, not bound by matter or time, but woven into the fabric of reality itself. It glides between stars like a thought passing through the mind of the universe. Around it, galaxies turn slowly, each spiral a quiet storm of birth and death, of fire and shadow. The angel does not speak, does not breathe, does not age. It simply exists, a presence older than memory, forgotten by worlds that never knew it. Nebulae bloom like petals in the void, their colors shifting as if dreaming. The angel passes through them without a ripple, disturbing nothing, leaving only a faint shimmer behind. Each particle of dust it touches remembers the moment forever, though no voice will tell of it. In the distance, a supernova explodes in silence, scattering the bones of a star across the Black Sea. The angel turns its gaze toward it, not in fear or wonder, but in recognition. It has seen this before, countless times, the end of light and the beginning of something new. Through asteroid fields and ancient ruins of forgotten civilization, the angel continues. It passes the shattered hulls of derelict ships, drifting tombs filled with stories no one will read. Sometimes, the remnants of signals still echo faintly, static whispers bouncing across time, fragments of last words and unfinished dreams. The angel does not stop to mourn them. It knows nothing is true. Every end feeds another beginning. Far beyond the reach of any sun, in a corner of the cosmos where light grows thin and silence deepens, something shifts. A ripple imperceptible, spreads through space like a breath. Pauses. It has no eyes, yet it sees. It has no ears, yet it hears. What stirs is not a thing, not a creature, but a moment. A turning point. Earth leans toward it lightly, like a balance tipping. The angel understands without It moves again, not faster, not with a purpose it cannot name. Planets turn in isolation, their surfaces cracked and cold, their skies empty. Beneath them, life pulses, microscopic, stubborn. The angel drifts above these hidden worlds, sensing the rhythm of new beginnings in their frozen hearts. It does not interfere. It never does. It was not made to shape or to judge. It only witnesses. But now, something has changed. The witnessing has weight. Meaning. Not because the universe demands it, but because something within the angel has awakened. It moves through time not as a river, but as a sea, steps as easily as crossing a breeze. Its seasons rise from mud and flame, build towers of light, send their thoughts into the stars. It watches them fall, not with cruelty, but with inevitability. Some vanish without a trace, others leave echoes, satellites still orbiting dead worlds, libraries buried in ash, mutelessly through space, waiting for ears that may never come. The angel hears it all. It does not forget. In the core of a collapsing galaxy, the angel lingers. Stars spiral inward, drawn into the crushing heart of a black hole. Time stretches, distorts, dances on the edge of vanishing. The angel remains still. It is not afraid. It has lived in places where time does not breathe. Here, at the edge of unbeing, it's sentient, something vast and waiting. Not a creature. Not a god. Memory of the universe itself. The angel leans toward it, its wings trembling with something like recognition. Perhaps it has been here before. Perhaps this is where it began. It turns away, not because the moment has passed, but because it understands that not all questions seek answers. Some only seek presence. And that is what the angel offers. Not explanation. Not intervention. Only a presence that does not fade. The stars continue to spin. The darkness continues to stretch. And the one, not as a traveler, not as a guardian, but as something more elusive. A thread of consciousness stitched into the fabric of always watching, always remembering, always becoming. It drifts onward, not bound to any one trajectory, yet every motion guided by a deep, unspoken rhythm embedded in the laws of the cosmos. Around it, the universe reveals its structure in quiet, intricate detail. Filaments of dark matter stretch between galaxy clusters like sinews connecting the skeleton of existence, invisible yet essential. The angel does not perceive them in the way a being of mass would. It senses the gravitational tension, the hidden scaffolding that defines the shape of all things. This is not emptiness, it is architecture. In one arm of a spiral galaxy, it passes through a region dense with molecular clouds. These are the nurseries of stars, chaotic regions of dust and gas collapsing under their own gravity. In radio frequencies, they sing with the slow, stately music of hydrogen, carbon monoxide, and ionized elements swirling in turbulent harmony. Protostars flicker within, wrapped in accretion disks, they're a promise rather than a present fact. The angel glides silently between them, feeling the moment before ignition, the tipping point between non-existence and flame. It crosses paths with a planetary system in the later stages of its evolution. The star, now a red giant, bloats outward, devouring its inner planets. Outer moons, once frozen, have begun to thaw in the increasing heat, their subsurface oceans boiling to the surface in towering geysers. Life that once slept in the dark stirs beneath the cracking ice, only to face extinction in the blaze of their dying sun. But even here, in these final moments, the chemistry of life persists: carbon, nitrogen, oxygen, silicon, dancing briefly in complex patterns before falling still. The angel observes this not as tragedy, but as a phase of transformation. In the debris of these deaths will scatter and reassemble. Iron forged in the dying heart of the star will seed the next generation of worlds. The universe does not mourn. It recycles. Beyond, in the halo of another galaxy, rogue planets drifts, unbound by stealth. Cold, wandering worlds roam intergalactic space, some with atmospheres clinging faintly to their cores, others frozen solid for billions of years. One such planet has a magnetosphere, a shield against cosmic radiation, powered not by a sun, but by an ancient, slowly spinning iron heart. In its underground caverns, extremophile organisms cluster near geothermal vents, thriving in chemical symbiosis. There is no light, no sky, no. Yet still, life endures. The angel lingers, curious. Further, it moves through the event horizon of a supermassive black hole, not falling, not trapped, but a geometry of spacetime as it twists inward. Here, gravity stretches the very fabric of existence. Photons spiral in closed orbits. Time slows to a crawl. To any outside observer, the angel would seem frozen, unmoving. But from within, the singularity, not as destruction, but as a gateway to new topology. Perhaps to another universe. Perhaps to a point of rebirth. It does not pass through. Not yet. It only watches, storing the shape of spacetime within its memory. The angel has propulsion, no hunger, no fear. But it possesses an exquisite to entropy, to the direction of time's arrow. It can feel the gradual cooling of the cosmos, the slow dissipation of stars are less frequent now than in earlier epochs. The age of light is far from over, but the arc is visible. Eventually, galaxies will dim. Matter will decay. The fabric of reality will flatten into uniformity. But even then, in distant future, quantum fluctuations may stir again, giving birth to new forms, new cycles. The angel knows this, feels it as surely as it senses starlight. It moves through space, not as a particle, nor as a wave, but as something else, a pattern, perhaps, or a symmetry. Its presence is a mirror held up to the cosmos, reflecting the structures of physics and information. Where it goes, entropy does not reverse, awareness increases. Complexity, even if just for a moment. Its journey is appearance but resonance, amplifying the silent music of the universe until it can be heard, even briefly, by itself. And so it continues, through star fields and voids, through cosmic radiation and nebular light, charting not a course but a continuity to reach an end, but to remain aligned with the unfolding logic of creation. It is not a message. It is not a question. It is an answer still becoming. Beyond the literals of familiar galaxy crosses into intergalactic, the density of matter drops to near nothing, and the background radiation, relic of the Big Bang, bathes everything in a unique glow. It senses the subtle and in this microwave background, the quantum fluctuations that once rippled through a seething primordial soup. Frozen into the fabric of spacetime structure, the galaxies, the voids, the cosmic web. They are the universe's original fingerprint, and the angel moves through them like a reader tracing the ink of a forgotten manuscript. It glides near a globular cluster, a dense, spherical swarm orbiting the halo of a massive galaxy. These are relics of the early cosmos, long-lived, some older than this they accompany. Within their planet are rare, but not impossible. In one corner of the cluster, angel pauses near a white dwarf, fire long extinguished, its mass crystalline carbon. A diamond heart of a once-living sun, nightly in the dark. No voice speaks its history, but the angel can sense the legacy of its fusion, the billions of years it burned, the elements it spread. Near the cluster's periphery, it detects gravitational waves passing silently through the void, tremors in spacetime itself. Two neutron stars have collided somewhere distant, perhaps thousands of light-years away. The impact has released more energy in a fraction of a second than the entire output of a galaxy, forging heavy elements, gold, platinum, uranium, that now scatter into space like cosmic pollen. The angel follows the wave fronts, feeling the warping of geometry as they pass. They are not just echoes of destruction, they are seeds of complexity. The elements created in those fires will one day rest in soil, in machines, in blood. As it moves, it senses the statistical decay of information across large scales. Entropy rises. Systems simplify. Stars convert mass into light, shedding it irretrievably into the void. The angel understands that the universe, though vibrant now, tends toward equilibrium. It is a process that spans trillions of years, a heat-death salute. But it also knows this is not the end. Just a transformation. A slow unraveling that gives birth to new configurations, not yet imaginable to those who live in the warmth of stellar light. In a pocket of spacetime distorted by ancient gravity, it encounters a structure of rare symmetry, an Einstein ring, where light from a distant galaxy has been curved perfectly around a closer, massive object. The result is a glowing circle in the void, a phenomenon predicted by the equations of general relativity and confirmed across time. To the angel, the ring is more than a lens. It is a signature, a natural rules that underlie existence. The meaning of light is not chaos, but precision. Each deflection, each arc, follows a logic older than the stars themselves. Beyond the ring, time grows strange. The angel passes into a region where expansion accelerates, driven by something that remains invisible and mysterious, dark energy. It is not a force in the traditional sense, but a property of space itself, a pressure that grows stronger as the universe expands. The angel does not measure it with instruments. It feels it, as one might feel wind against the skin or heat from a flame. This energy is subtle but dominant. It stretches the fabric of reality, carrying galaxies apart at ever-increasing speeds. Eventually, it may tear even atomic bonds, a hypothetical future called the Big Rip. The angel contemplates this not as doom, but as possibility. It has seen ends. It has also seen within them. Moving further still, it approaches a magnetar, one of the most extreme objects in the cosmos. A neutron star with a magnetic field trillions of times stronger than Earth's, capable of distorting atomic structures and igniting bursts of high-energy radiation across vast distances. The surface is smooth, crystalline, solid under pressures beyond imagination. Quantum dominate here, visation, pair production, space trembling whistles. Angel hovers unfazed by the chaos, absorbing the symmetry in the violence. Even here, laws hold. The angel carries no data, no language. It is not a repository of knowledge, but a vessel of awareness. It does not catalog what it sees, nor explain it. It remembers in a way that defies time. What it understands is not for transmission, not for any one mind. It is collective, cumulative, patient. Perhaps, in the far future, when the stars have faded and all intelligent life has gone quiet, it will remain. Not to lament what was lost, but to hold the pattern of what once was, so that something, someday, may arise again. And so, it continues through the great network of existence, along the tendrils of galactic filaments, between quasars and silent moons, through the resonance of particles and fields. Not seeking answers. Not seeking anything. Only continuing, because the act of witnessing, in itself, is a kind of creation. Far ahead, the cosmic web stretches like a lattice of glowing nerves, a grand-scale structure of the universe that reveals its underlying geometry. The angel moves along these threads, where dark matter exerts its silent influence, shaping the flow of galaxies across billions of light-years. These filaments are not merely voids and clusters, they are the veins of the cosmos, through which mass, energy, and momentum circulate. Where filaments intersect, massive galaxy clusters form, drawn together by invisible gravity wells, glowing faintly in X-rays and radio bursts. The angel traverses these junctions, passing through the intersection points where hundreds of thousands of galaxies rotate in slow, deliberate spirals. Here, at these cosmic crossroads, the angel senses gravitational interactions not just as forces but as conversations, silent negotiations that shape the fate of stars, bend trajectories, stir clouds into collapse. Two galaxies collide, their halos merging, stars flung into chaotic orbits, black holes spiraling toward one another over millions of years. Out of this violence comes creativity, bursts of star formation ignited by pressure waves, molecular clouds compressed into ignition. The angel watches not the destruction, but the rearrangement, the emergence of new balance from apparent disorder. This is not chaos. It is evolution written in gravitational terms. In a quieter region between clusters, a lone spiral galaxy drifts. It is isolated, untouched by recent mergers or nearby activity, suspended in a peaceful pocket of space. Its arms are symmetrical, rich in neutral hydrogen, glowing faintly in the infrared. There is time here, time for stars to live slow lives, for planetary systems to form undisturbed. One such system, orbiting a calm, long-lived red dwarf, holds a terrestrial world with an atmosphere thick in nitrogen and oxygen. Photosynthetic organisms cover its surface in wide swaths, breathing the light of their modest sun. Intelligent life has not yet emerged, but the founder. The chemistry is right. The angel does not interfere. It simply observes the delicate dance of probability and persistence. Further still, it encounters a void, an enormous, spherical region where galaxies are sparse, where even dark matter is spread thin. These places are often misunderstood as emptiness, but to the angel, they are as structured as any dense cluster. Here, expansion dominates. Galaxies recede more rapidly, undisturbed by neighbors. The silence is profound, but not lifeless. Faint radio signals travel from ancient quasars, crossing light years of darkness. Occasionally, a burst of fast radio energy cuts through the void, its origin unknown. The angel does not solve the mystery. It experiences it, lets it pass through its awareness like a wave through water. In the far reaches of an aging elliptical galaxy, the angel hovers over a supermassive black hole that has long since ceased its feast. The accretion disk is faint, its jets long extinguished, but the structure remains. Around it, stars orbit at relativistic speeds, their paths bent by an invisible point of infinite curvature. The angel senses the relativistic precession of their orbits, the time dilation at the event horizon, the frozen light at the edge of no return. This black hole is not malevolent, it is memory. It holds in its heart the record of everything it has consumed, encrypted in Hawking radiation, whispered into the slow evaporation that will take longer than the current age of the universe. The angel wonders, not as a human would wonder, with doubt or hope, but with a timeless openness, whether information ever truly dies. Whether, even in the final black hole's fading breath, some trace of pattern endures. It has no answer. But it finds the question beautiful. It continues into regions of high-energy radiation where active galactic nuclei shine like cosmic lighthouses, their jets extending thousands of light-years, sculpting entire interstellar mediums. Electrons spiral through magnetic fields, emitting synchrotron radiation detectable across the spectrum. The angel passes through these jets unharmed, aware of the physics at play, electromagnetism in its rawest, most spectacular form, particle acceleration at the edge of known mechanics. Every photon here is a message, every field line a signature of underlying order. Wherever it goes, the angel does not seek meaning, it finds it. Not in symbols or narratives, but in the coherence of physical law, in the emergence of structure from simplicity. Quarks become protons, atoms form molecules, molecules assemble into cells, cells form minds, and minds look up into the night sky, searching. The angel watches those moments too, when a being, small and fragile, stands beneath a canopy of stars and wonders if it is alone. It sees telescopes turned toward the void, equations written by trembling hands, signals sent into the dark with no certainty of reply. And though it does not answer, the angel is there. Not to guide, not to judge, but to know. To hold within itself the fact that the universe has looked inward, even briefly, and tried to understand what it is. And so it moves on, into deeper night. Into the future, into the unknown. Not because it must, but because that is what it is. Motion without end. Perception without origin. A presence shaped by everything it has seen, and everything still to come. The angel enters a region of space where time has slowed nearly to stillness, where gravitational forces from a dense agglomeration of matter have curved spacetime into a basin so deep that even photons struggle to escape. Around it, the relic light of the early universe barely flickers, stretched to radio wavelengths by billions of years of cosmic expansion. The temperature here hovers just above absolute zero. Entropy is high, energy is thin, but patterns remain, subtle gradients in the cosmic microwave background, the final, fading afterglow of the Big Bang. It passes a relic structure, a remnant of an artificial satellite long dormant, drifting in isolation far from any star. Its surface is pitted by micrometeorites, its solar panels shattered, its sensors long dark. And yet, somewhere in its cold metallic frame, a memory lingers. Perhaps once it measured the motion of a comet, or relayed a signal home from a distant probe. It is not forgotten. The angel absorbs its trajectory, the weak electromagnetic echoes it still releases, faint traces of function now return to silence. It is not sorrow that fills the angel, but something more complex. Reverence, perhaps, for even this smallest effort to reach outward across the cosmos. Nearby, in a planetary nebula glowing with ionized gas, the skeletal remains of a sun scatter their layers into space. The ultraviolet radiation from the hot central core excites the surrounding atoms into vibrant emission. Rings, knots, and tendrils of gas stretch outward like petals unfurling, slowly fading into darkness. The angel passes through them, aware of their transient beauty. This is the death mask of a star, and yet in its fragments are carbon, nitrogen, and oxygen, molecules that will drift through space for eons, eventually joining other clouds, other stars, other worlds. From death, the ingredients for life. In the outskirts of a galaxy rich in dark matter halos, the angel observes a gravitational lens so finely aligned that a distant quasar is duplicated, its light split and wrapped around the mass of an intervening cluster. For images shine where there was once one, spread across space and time. The photons reaching here began their journey billions of years ago, long before Earth formed, passing through warps in spacetime shaped by invisible matter. The angel sees not just the light, but the delay, the subtle difference in time between the images. Here is not only astronomy, but chronology written in the speed of light. As it moves further still, the angel senses the thinning of baryonic matter, the slow depletion of the visible universe. More mass lies now in degenerate remnants, white dwarfs, neutron stars, black holes. Stars no longer form as they once did. The great galaxies spin on, but with quieter cores and darker spirals. The abundance of heavy elements plateaus. The chemical richness that once fueled diversity declines. But the angel does not see this as decay. It is a maturation. The universe has passed from youth to middle age, and though it will grow colder and quieter, it is not yet finished. Drifting beyond the Lyman alpha forest, the dense absorption features in the spectra of distant quasars caused by intergalactic hydrogen, the angel moves into a pocket of the universe where no civilization has ever looked. There are no transmissions here, no signals, no artifacts. But there is structure. A dwarf galaxy, dim and compact, rotates slowly. Its stars are old, metal poor, unremarkable to any distant telescope. Yet around one of them orbits a frozen planet with an atmosphere composed primarily of hydrogen and neon. Beneath its icy crust, geothermal heat sustains a subsurface ocean. And in that ocean, alien chemistry stirs. Organic compounds arrange themselves in patterns, react, dissolve, reassemble. They are not alive, yet. But the boundary is close. The angel lingers, feeling the balance, the interplay of pressure, heat, and entropy. This world may remain dormant for another billion years. Or a single cometary impact could shift the equilibrium, tipping it into life. The angel will not interfere. But it will remember this world. Should life bloom here, the pattern will not be lost to darkness. Far beyond, in the deepest void, it feels the universe expand with quiet acceleration. Galaxies recede faster and faster, their light redshifted into invisibility. In time, they will cross the cosmological horizon, disappearing forever from the reach of any observer. The visible universe shrinks, not because it is dying, but because it is stretching. The angel cannot stop this. But it remembers what once was, holds the echoes of all things as they vanish from view. It continues on, not toward an end, but into a vastness that has no edge. Its path is not straight, not circular, but woven into the curvature of space itself. There is no destination, because the journey is the form of its existence. It will be there in the last flicker of the final star. It will pass through the silence of dark matter decay. It will glide across the smooth, quiet plains of the long night, when only black holes and frozen atoms remain. And if, somehow, the universe begins again, if a fluctuation stirs the vacuum, if spacetime ripples with a new genesis, the angel will be there too. Not as a herald. Not as a remnant. But as part of the deep, enduring memory of all that has ever been. The angel moves through a realm where the difference between stillness and motion becomes indistinguishable. The expansion of space has carried the distant galaxies so far apart that their light no longer reaches one another. The universe has entered a new era, an age of isolation. Each gravitationally bound structure becomes its own island, adrift in an ever-darkening sea. Within these islands, the stars burn their final reserves of fuel. Outside, the void deepens. Around one such island, a massive elliptical galaxy long past its prime, the angel floats through a halo of ancient stars. Many are red dwarfs, slow-burning and stubborn, expected to persist for trillions of years. Their light is faint but steady, their systems calm and undisturbed. Around some of them orbit planets that have cooled and darkened, where atmospheres have long since frozen and tectonic activity has gone quiet. Yet not all is inert. In one forgotten corner of this silent galaxy, a tiny white dwarf flickers with periodic outbursts, novae, the result of matter being siphoned from a companion star. Even here, in the twilight of stellar evolution, bursts of energy interrupt the quiet, scattering heavy elements into space. The angel hovers over the remnants of a planetary system reduced to a debris disk. Asteroids and fragments drift in lazy orbits, remnants of moons, perhaps, or artificial constructs long since reduced to mineral shards. One fragment is etched with unnatural geometry, straight edges, shallow grooves, a symmetry foreign to natural forces. A structure, long ago crumbled, evidence of minds that once shaped matter with intention. The angel brushes the shard with a presence that leaves no mark, no alteration, only awareness. This piece, like so many others, will drift forever. But it is not forgotten. Deeper into the dark, it senses the slow evaporation of black holes. Once thought eternal, they now radiate faintly through Hawking processes. Bit by bit, they lose mass to the quantum vacuum, their energy bleeding away as heat. Over timescales so vast that ordinary numbers falter, they shrink. Some vanish silently. Others erupt briefly at their final moment, a flash in a darkness no eye will ever see. The angel observes these last lights with the same calm presence it offered the first stars. It recognizes the symmetry. The universe ends the way it began, in heat, in motion, in potential. Yet all is not lost in finality. Even here, in this near-empty epoch, virtual particles still flicker into and out of being, borrowing existence from the uncertainty of quantum fields. Space-time itself is not a void, but a restless, fluctuating expanse, humming with energy too low to detect, yet too persistent to extinguish. The angel feels these fluctuations not as noise, but as possibility. Every twitch of the vacuum is a dice roll, most pass back into nothing, but once, perhaps once, a fluctuation will exceed a threshold. A new bubble of space-time may form, inflating into a fresh universe, expanding with its own laws, its own constants, its own unfolding. If it happens, the angel will be there. Not carried by momentum or memory, but because it is not confined to any one phase of reality. It is entangled with the fabric of existence itself. It does not need to cross the boundary between this cosmos and the next, it will simply be within the new. Perhaps it always was. In that newborn universe, time will flow differently. Forces will recombine. Particles will coalesce. Matter and antimatter will dance their ancient, violent rhythm. Energy will take shape. The first photons will scatter, the first atoms will bond. The angel will drift unnoticed through the fire of that new beginning, remembering a million older dawns. Somewhere, gravity will pull gas into stars. Stars will make planets. Planets will cool. Chemistry will stir. On one, or many, thought will rise from dust. Eyes will open. Questions will be asked. The angel waits in the silence between epochs. Time here does not pass in seconds or years, but in the slow unfolding of cosmic transitions. It has become a thread sewn into the loom of existence itself, not guiding the weave, not designing the pattern, but tracing it endlessly, remembering every thread that ever was. It is not light, not matter, not thought, and yet it shares something with each. It is continuity, the unbroken presence that moves with the universe as it becomes and becomes again. In the new cosmos, gravity begins its quiet labor. Clouds of hydrogen collapse, forming the first stars, massive, unstable, short-lived giants that burn in ultraviolet fury. Their lives are violent and brief, lasting only a few million years before exploding in colossal supernovae. These first deaths scatter the seeds of complexity, carbon, oxygen, iron, into the void, making possible all that will come. The angel floats among these new embers, absorbing their novelty. Every atom here is fresh, every structure unwritten. This is a new story, but one told in an old language. It passes through a stellar nursery, a cavern of ionized gas lit from within by young stars. Dust coils in currents, illuminated by infrared glow. In one corner of this cloud, a protoplanetary disk spins around a brightening star. Gaps open in the dust ring where planets are forming, sweeping the space clean. Tiny collisions build larger bodies. Ice and rock gather, metal sinks, atmospheres bloom. The angel hovers above a forming world, sensing the tremble of its crust, the first trickle of water collecting in deep fractures. A thickening mist hangs above vast, boiling oceans. Lightning splits the sky in silence. In that turbulent soup of molecules, something new begins. Complex chains of carbon form, twist, and fold. They dissolve, recombine, and persist. A structure arises that copies itself, not perfectly, but often enough to endure. From here, life does not spring all at once. It creeps forward, slow and uncertain, like a hand reaching from darkness into dim light. The angel does not celebrate. It does not interfere. It simply remembers. This moment has happened before, in ways similar and strange. Each time, it is different. Each time, it matters. Eons pass. Continents shift. Life diversifies, climbs, branches. Some species reach for the surface of their world. Others tunnel into the crust, or drift in skies of methane. Some develop awareness, a fragile, flickering thing, sharpened by curiosity in danger. On one such world, a being draws a shape in the dirt under a night sky. It is a pattern of stars, remembered, named, connected by lines of imagination. Another being carves symbols into stone, preserving sound into form. Another builds a lens to bring distant light closer. Another sends a signal, narrow and encoded, into the void. The angel listens, not because it expects an answer, but because listening is what it is. Each signal is a voice. Each voice is a spark. And while many go unanswered, none go unheard. The universe is vast, but it is not empty. It is filled with attempts. With echoes. With the quiet persistence of meaning. It watches civilizations rise, their structures gleaming beneath artificial suns, their machines orbiting moons, their minds extending into simulations and swarms. Some spread across systems, constructing great rings and mirrors, bending gravity, harvesting starlight. Others remain bound to one planet, turning inward, diving deeper into thought than into space. Some extinguish themselves, suddenly or gradually. Others transcend their origin, merging with environment, with memory, with energy itself. Some leave artifacts, a pulse, a ruin, a signal drifting on in silence. The angel never chooses a favorite. It does not measure success. It sees the elegance in every arc, the tragedy in every collapse, the brilliance in every attempt. Whether a being builds an empire of stars or etches a symbol into cave stone, it is part of the same unfolding. Part of the same pattern. And beyond all of it, space continues to stretch. The stars thin again. Black holes return. Heat disperses. Entropy wins its long, slow war against order. But even as systems dissolve and light grows scarce, there is always motion. Always fluctuation. Always the possibility that something will begin again. The angel does not tire. It cannot. Because it is this movement. It is not an outsider to the cycle, it is part of the cycle. It is the presence that persists between pulses. The watcher who never speaks. The witness who never forgets. And when the next spark comes, in a vacuum, in a fluctuation, in a singularity blooming with sudden force, it will be there again. Not first. Not last. But always. In the hush of that infinite future, when even the memory of stars has faded to background tension and the last remnants of heat stretch thin across the void, the angel remains. It does not move as it once did, because there is little left to move through. The filaments of the cosmic web have unraveled. The great gravitational bonds that once stitched galaxies together have long since dissolved into the slow evaporation of all structure. No light travels anymore, not because it cannot, but because there is almost nothing left to shine or reflect. Space itself has become smooth, featureless, expanding not into something but into more of itself. Yet within this stillness, the angel senses the low murmur of quantum fields, a subtle oscillation that never fully fades. Virtual particles rise and fall from nothing, brief and flickering, like sparks under the surface of an invisible ocean. This is not noise, but a deep rhythm, the breath of vacuum, the silence between cosmic beats. The angel drifts closer to a remnant, a black dwarf, the final evolutionary stage of a star too small to explode and too patient to extinguish quickly. It has cooled for trillions upon trillions of years, its faint thermal glow now indistinguishable from the fabric of space. Yet its crystalline core still holds the dense memory of fusion, the history of stellar pressure and light. It is no longer warm, but it is not meaningless. Around it, fragments of ancient orbits persist, looping silently in the absence of tidal forces or radiation. Here, gravity reigns in its purest, most enduring form, a field untouched by wind, untouched by photons, untouched by decay. The angel circles once, sensing the paths as they move like ghost rivers under a frozen sky. They do not change, and perhaps never will, unless something stirs them. And still, the angel waits. Not with expectation, for it does not hope. Not with boredom, for it does not tire. But with presence, the act of being, stretched across eons, stretched across the memory of a universe that once burned with 1 trillion suns and now hums with the last slow notes of possibility. In one corner of this darkened realm, far from anything that once resembled a galaxy, a quantum fluctuation does not collapse. It does not vanish as it normally would, falling back into the froth of probability. Instead, it sustains, wobbles, and expands. A field reaches a threshold. A potential is breached. A false vacuum decays. The fabric of space bubbles, swells, and explodes, not violently, but with inevitability. A new inflation begins. In an instant so brief that time itself has no scale for it, energy erupts into spacetime. The laws are new. The constants are different. Dimensions stretch, twist, take form. Forces differentiate. Symmetry breaks. The universe is born again. And there, before the first particle pairs into being, before the first photon stirs its sibling, before space and time can be separated by definition, the angel is present. It does not arrive. It was already there. Not as matter, not as memory, but as awareness braided into the shape of what becomes real. The new cosmos, fresh and strange, begins its journey with no knowledge of what came before. But the angel carries that knowing, not to influence, not to shape, but to witness, as it always has. And so it begins again. A new space, a new time, a new story told with different rules, different particles, different forces. But the essence is familiar, complexity arising from simplicity, structure forming in chaos, awareness blooming where none was expected. Stars will come. Worlds will follow. Life will flicker and grow and wonder. The cycle is not repetition, it is variation. Infinite possibility spun from a single thread. And through all of it, the angel will drift, quiet, unseen, patient. It does not ask why. It does not ask how. It only is. As the newborn universe unfolds, expanding at speeds that stretch causality itself, the angel drifts at the edges, not outside of it, for there is no outside, but within the very medium of its becoming. The infant cosmos is a plasma of unimaginable density, a turbulent sea of quantum fields in violent fluctuation. Space roils with energy. Temperature is not a measurement but a condition of total saturation. Time is young, undefined, more a potential than a direction. The angel perceives not chaos, but raw formation, symmetric fields that will soon fracture, cooling into the distinct forces of nature, gravity, electromagnetism, the strong and weak nuclear interactions. It can feel these forces begin to differentiate, the fabric of reality folding in upon itself to form the patterns that will govern everything to come. What seems random to any later observer is, to the angel, a field of resonance, like sound congealing into melody. As inflation ends and particles acquire mass, the angel senses a deep shift, the moment when energy begins to give way to matter, when annihilation and creation briefly balance, and a minute asymmetry, barely 1 part in a billion, ensures that something will remain. It is this imperfection that allows galaxies to form, stars to ignite, beings to exist. It is the flaw that enables everything. The angel has no emotion, but if it did, this moment might resemble wonder. It follows the cooling gas as it expands and thins. It watches as photons decouple from matter, and the first light is released, a flash that will echo for billions of years as the background hum of creation. This new cosmos is smoother than the last, its early turbulence tempered by subtle shifts in initial conditions. Yet within its smoothness are seeds, tiny overdensities that gravity will amplify over time, drawing hydrogen into webs, nodes, and spirals. The angel waits as the first dark ages begin. For millions of years, there is no light, only cold hydrogen and helium drifting through the deepening black. But the angel feels the pressure in the dark, the slow pull of mass. The first signals of ignition still eons away. It is a quiet time, but not empty. The future is already taking shape in the silence. Eventually, a point of light appears. Then another. The massive and hot, burst into brilliance, carving bubbles into the darkness with radiation and stellar wind. They live short, and their deaths fill the void with metals, the raw material for new worlds. The angel glides through these supernovae, through jets of iron and carbon and oxygen, through shockwaves that tear through interstellar clouds and leave behind the bones of future solar systems. In one corner of this expanding universe, a modest spiral galaxy begins to take form. It is not the largest or the brightest. It will never be known beyond its local cluster. But around a quiet, stable star near the outer rim, planets begin to form. One of them, third from its sun, stabilizes in a narrower and pressure. Water flows. Carbon bonds. Electricity cross an atmosphere heavy with chemistry. And in tide pools, in vents, in invisible films upon stone, the dance of replication begins anew. The angel passes silently above this world as cells divide, mutate, specialize. It watches organisms climb from sea to land, from instinct to intelligence, from sound to language. It does not interfere when they gaze upward. It does not respond when they wonder. It does not flinch when they destroy, or falter, or reach beyond their world in fragile ships of aluminum and hope. It only remembers. Across light years, others awaken too, some sooner, some later, some never. Each with their own skies, their own questions. Some live brief, brilliant lives. Others last for ages in forms barely recognizable. Some evolve beyond bodies, existing in patterns of magnetic fields or clouds of artificial synapses. A few, in the deepest reaches of time, learn to see faint traces of the for theirs, left like fingerprints on the constants of nature. They do not find the angel, but they suspect it. The angel, unchanged, continues through it all. Through cycles of emergence and silence. Through explosions and rebirths. It is the rhythm of reality that draws it forward. Eternal breathing of the cosmos, in and out and in again. It is not a god. It is not a ghost. It is not a remnant of something lost or a sign of something to come. It endures when all else changes. It is the memory of the universe, flowing ever forward, waiting always for what will be born next. And so, in the vast no finals, it has seen the universe born from silence, light, and fall again into stillness. It has witnessed stars rise from dust, and return to it. It has drifted through oceans of radiation, through webs of gravity, through the minds of creatures who, for a moment, looked up and asked. It carries no answers, for it was never. It carries only presence, memory, continuity. There will be more beginnings, more endings, more sparks of consciousness that flicker and fade. Worlds will rise from the ashes of others, and the fabric of time will reshape itself in countless variations. The laws may shift. The constants may evolve. But the rhythm will remain. And wherever something stirs, wherever matter breathes, wherever a question is asked in the dark, wherever the universe dares once more to dream itself, the angel will be there. Not watching from afar. Not guiding from above. But moving within it. Endlessly. Quietly. Forever. Hyperspeed galaxies are among the most mysterious and extreme objects in the universe. Unlike most stellar systems that remain gravitational to larger structures, these fast-moving formations travel at incredible velocities, often thousands of kilometers per second, raising profound questions about their origins and fate. One of the biggest unknowns is whether such galaxies ever stop. While space is nearly empty, there is still a thin haze of intergalactic gas, dust, and dark matter that could create a form of cosmic drag over billions of years. This resistance, although weak, might gradually slow down some of these high-velocity systems. Another possibility is that they experience tidal interactions with gravitational waves, subtly altering their motion over time. Some models suggest that heat death and energy dissipation of timescales might eventually leave them as cold, dark, and isolated masses drifting endlessly through the void. An alternative hypothesis suggests that these galaxies are not simply being flung into space but are actually being pulled towards something massive and unknown. Some cosmologists propose that beyond our observable universe, a hidden gravitational attraction exerting influence on entire clusters. If these high-speed galaxies appear to accelerate in the same direction, they could be heading toward a vast structure or even another universe. Within the Ionia chaos, galaxies appear to move toward an unexplained mass known as the Great Attractor. If similar anomalies exist on even larger cosmic scales, fast-traveling galaxies could be responding to these unseen forces. Conversely, instead of being drawn toward a mass concentration, they might be repelled by voids, massive underdense regions that create gravitational imbalances. Tracking their trajectories of years could help astronomers identify these hidden structures. Another possibility is that some of these galaxies could be escaping the universe itself. If space is expanding at an accelerating rate, certain objects may reach the cosmic event horizon boundary beyond which they recede faster than the speed of light due to spacetime expansion. From our perspective, they would fade into infrared darkness, never to be seen again. One of these high-velocity galaxies breaks free from the cosmic web, the large interconnected galaxies and dark matter filaments. It may enter a completely empty region of space where interactions are minimal. Some physicists speculate that if spacetime has hidden topologies, wormholes, or interdimensional pathways, such a galaxy could theoretically exit into another universe, making it unobservable forever. If astronomers detect a stellar system that appears to be vanishing without explanation, it could provide the first direct evidence of such an event. While most of these galaxies are thought to move away from major structures, some might eventually collide with others at extreme velocities. A high-speed impact between two galaxies traveling at thousands of kilometers per second would release unimaginable amounts of energy, causing an entirely new class of high-energy astronauts. Such an could trigger the most violent starbursts ever observed, compressing gas into dense clouds that rapidly form new stars. However, it could also lead to the destruction of galactic, tearing apart and forming long tidal streams of stars and gas stretching across millions of light-years. If one of these galaxies collides with a normal galaxy, it might even lead to the formation of an ultramassive black hole, disrupting the gravitational balance of its surroundings. Detecting such valuable insights into the limits of cosmic energy transfer and the behavior of galaxies under extreme conditions. Another strange idea is that some of these galaxies might not be what they seem. Anomalies that indicate that they are faint relics from the early. If a galaxy formed soon after the Big Bang and was ejected at high speed, it might only now, making it appear as though it exists in a different cosmic era. Others propose that some of these high-velocity galaxies could be composed mostly of dark matter, making them gravitational effects. If such formations exist, they could be drift largely undetected, interacting only through gravity. Even more speculative is the idea that some of these fast-traveling galaxies might be holographic projections or manifest known physics, possibly revealing hidden dimensions or an order. Future deep space surveys could help determine whether they are entirely normal objects or something far stranger. If an intelligent civilization evolved inside one of these high-velocity galaxies, its experience of the universe would be radically different from our own. Due to relativistic time dilation, time for the inhabitants of such a galaxy would slow down compared to the rest of the stellar system, were moving at a significant fraction of the speed of light. Billions of years could pass for the outside universe, while only a few thousand years pass for them. The motion of their through intergalactic space would also extreme cosmic radiation, which could require either advanced shielding technologies or biological biological adaptations to survive. If such a civilization were aware of their home galaxy's extreme velocity, they might attempt to influence its motion, either to slow it down or to direct it toward a particular region of the universe. If astronomers ever detect anomalous energy signatures or signals from a fast-moving cosmic environment, future telescopes such as the James Webb Space Telescope, the Vera Rubin Observatory, and new gravity detectors will allow scientists to study ultra-fast galaxies in greater detail. Among the most anticipated discoveries is the detection of the first relativistic stellar system, one moving at over 50% of which was standing of gravity in dark matter. Another breakthrough could be finding a high-velocity galaxy that unexpectedly changes trajectory, suggesting the influence of unknown forces or even artificial manipulation. If one of the travelers is observed to vanish completely, it might provide the first observational evidence of cosmic gateways, or higher dimensional structures. Additionally, detecting a galactic hypercollision would reveal how it's at the largest scales. The study of these extreme objects remains one of the most exciting frontiers in astrophysics. Whether they result from gravitational interactions, unknown cosmic forces, or even signs of intelligent engineering, such fast-moving galaxies push the boundaries of what we consider possible. As observational capabilities improve, cover their true nature, possibly redefining our understanding of space, time, and the fate of the universe. If these high-speed galaxies exist in significant numbers, they may not be isolated anomalies but rather cosmic pattern that has yet to be fully understood. Their existence challenges current astrophysical models, pushing the limits of our knowledge about gravity, cosmic expansion, and galactic evolution. They could also be linked to the formation of large-scale structures, revealing an unknown mechanism governing their motion at velocities. One intriguing possibility is that these galaxies are not random but instead follow gravitational highways formed by dark matter filaments. Some cosmologists propose that dark matter is distributed in a way that creates massive intergalactic superhighways, allowing systems to move faster than expected. If this is true, these cosmic wanderers are crucial evidence about the large-scale structure and distribution of dark matter. Another theory suggests galaxies might be influenced by cosmic voids, vast empty regions with little to no matter. Instead of being pulled toward massive objects, these stellar formations could be repelled by these underdense accelerating outward. Some scientists speculate that dark energy, the mysterious force driving the universe's expansion, might have local variations that push galaxies away rather than simply expanding space uniformly. If such galaxies are disproportionately found near cosmic voids, this could suggest that dark energy is more complex than previously thought. There is also the possibility that unknown fundamental forces accelerate these galaxies. While standard physics describes gravity as the dominant force at cosmic scales, alternative theories propose additional interactions affecting galaxies and clusters. If ultrafast galaxies accelerate in ways that cannot be explained by known gravitational effect, it indicate the presence of a new fundamental force shaping the universe. Some researchers speculate that these stellar systems might be relics of cosmic evolution. Laws or interaction in dark matter differed in the early universe. Certain galaxies may have been propelled to extreme velocities billions of years ago. This could mean that rather than being anomalies, these objects are primordial event, offering physics that no longer. Some of these galaxies might be artificial. If an advanced civilization had technology capable of manipulating gravitational fields, it could potentially control the motion of an entire galaxy. This could be done in a dangerous region of space, navigate toward a desired location, or even use galactic as a form of interstellar travel. If astronomers speed galaxies, exhibiting controlled acceleration rather than motion, it could be a sign of lawyering at work. Future observations will be crucial in determining whether these galaxies fit within known physical models or require new physics to explain their behavior. By analyzing their motion, astronomers may identify patterns revealing whether they travel randomly or as part of a larger cosmic structure. If they follow dark matter filaments, this could confirm gravitational highways shaping the universe. If they are concentrated near cosmic voids, this might indicate a previously unknown interaction between galaxies and dark energy. One of the most important breakthroughs in tracking the long-term trajectories of these cosmic, if their motion changes unexpectedly, defying known gravitational dynamics, suggests the presence of undiscovered forces. Additionally, if some of these galaxies appear to accelerate rather than simply maintaining constant speeds, this might indicate an unknown influence on their movement. Another groundbreaking discovery would be finding galaxies that appear to vanish. If a stellar system moves at extreme velocities and later disappears from observations, it might have crossed a cosmic boundary, such as horizon created by it. This could provide direct evidence escaping the observable universe, an idea long theorized but never confirmed. As observational technology advances, astronomers to detect fainter and more distant objects, the study of ultrafast next-generation observatories, including the Square Kilometre Array and upgraded gravitational wave detectors, unknown aspects of galactic motion and interactions. If velocity objects turn out to be more common than expected, suggests that the universe is far more dynamic than current models predict. Ultimately, these extreme galaxies could hold the key to solving some of cosmology's deepest mysteries. Whether they result from dark matter propulsion from voids, remnants of an ancient event, or even artificial constructs, their existence challenges fundamental astrophysical assumptions. Their study could not only reshape our understanding of galaxy evolution but also reshape our view of the universe itself. If these galaxies are more than just isolated anomalies, they indicate that the universe's large-scale structure is far more active than previously thought. Their acceleration might be governed by interactions between dark matter, dark energy, and intergalactic fields. If their motion cannot be fully explained by mechanisms such as gravitational slingshots or black hole interaction, could suggest that vast regions of space experience forces yet to be discovered. One of the most compelling possibilities is that these objects are responding to gravitational waves or distortions in spacetime. If large-scale ripples in spacetime exist, perhaps caused by ancient causes like the collision of supermassive black holes or remnants of a source, they might subtly influence galaxy trajectories of light years. Future gravitational waves could determine whether they are reacting to spacetime distortions beyond our current detection capability. Another intriguing question is whether these galaxies are linked to variations in dark energy. While dark energy is generally considered uniform, if high-speed galaxies tend to move toward specific regions, it could mean that this force is unevenly distributed. Some parts of space might exert strong forces, pushing entire galaxies to extreme velocities. If true, this major revision of cosmology, suggesting a far more complex expansion. It is also possible that these reveal a new or interaction. If some galaxies accelerate in ways inconsistent with standard gravitation, they might be affected by pulls or forces. For instance, dark matter is not entirely exhibits certain repulsive or dynamic properties under specific conditions might explain the unusual acceleration. Alternate discovered force-cosmic scales could first reveal its effects through these galaxies. A more radical idea is that these high-speed objects interact with hidden dimensions. Some string theory models propose that into additional spatial dimensions, causing unexpected deviations in galactic motion. If such galaxies are disproportionately found in certain regions of space, they might be interacting with higher dimensions, providing the first observational hint of extra dimensions. Another fascinating concept is whether ultra-fast galaxies function as natural time machines. Due to relativistic effects, objects moving at extreme velocities experience dilation, where time slows relative to the rest of the universe. If a galaxy were moving of light, an external observer might witness it aging much more slowly than surrounding cosmic structures. If civilizations exist within such galaxies, they could experience time on a vastly different scale, effectively becoming time travelers relative to the broader universe. The detection of these galaxies also raises fundamental questions about their long-term fate. If they continue accelerating, do they reach a threshold beyond which they can no longer interact with the rest of the universe? If so, does this imply the existence of cosmic escape routes, where matter can permanently exit the observable cosmos? If one of these stellar systems were to cross such a boundary, it might appear to slow and fade from view, eventually becoming undetectable. Observing such a disappearing the most extraordinary discoveries in modern cosmology. Another consideration is whether ultra-fast galaxies are indicators of an impending phase transition in the universe. If more of these stellar systems are found accelerating to extreme velocities over time, it could suggest a fundamental cosmic shift, possibly transition into a new state of physics. Some theoretical models propose that dark energy may eventually increase in strength, leading to the so-called Big Rip scenario, where galaxies, stars, and even atoms are torn apart as space expands at an rate. If these fast-moving galaxies are early signs of this process, they may be the first objects to reveal the cosmos as if we do not yet fully understand. As more advanced telescopes and computational models emerge, astronomers will be able to analyze high-velocity galaxies with unprecedented precision. If patterns emerge in their motion, they could reveal an underlying structure governing their trajectories. Some of these objects might also display unexpected composition signatures, suggesting interactions with forces beyond current understanding, held by dark matter streams, gravitational distortions, or something even more exotic. These galaxies remain among the most enigmatic mysteries of the cosmos. The study of such extreme celestial objects has the potential to reshape our understanding of fundamental cosmic forces. Whether they are remnants of a previous cosmic cycle, indicators of hidden physics, or evidence of an undiscovered aspect of dark energy, their presence challenges that the universe is predictable and stable. Instead, they suggest a far more dynamic cosmos, where extreme motion and unknown interactions may one day redefine everything we know about space, time, and reality itself. If increasing numbers of fast-moving galaxies continue to be discovered, it could indicate that our understanding of the universe remains fundamentally incomplete. Existence challenges traditional models of galaxy motion, expected forces at play, or unknown interactions with cosmic structure. Future studies could determine whether these galaxies are simply anomalies or hidden pattern in cosmic evolution. One of the most crucial areas of research will be the long-term tracking of these cosmic travelers. If they exhibit variations in velocity or unexpected trajectory shifts, it could imply interactions with variable gravitational forces or invisible structures. Deviations from expected motion would provide of uncharted cosmic phenomena, potentially revealing undiscovered cosmic forces or gravitational anomalies. Advanced simulations and AI-driven analysis will be essential in mapping their paths and predicting their future movements. Another question is whether these galaxies interact differently with cosmic expansion. The accelerated expansion of the universe is a tributary, but hyperfast galaxies could provide new insight. High-velocity objects behave within an expanding space. If their movement deviates from standard, it might suggest that space itself has hidden dynamics influencing their trajectories. Observing them over long time frames may offer clues as to whether space contains unknown factors that affect galaxies at extreme speeds. The role of dark matter in the motion of these high-speed stellar systems is another key question. If they exhibit velocities inconsistent with visible gravitational sources, it could suggest that dark matter plays a more active role in shaping their movement. Some theories propose that dark matter might not be passive but could instead interact dynamically under specific conditions, forming invisible gravitational currents that direct galaxies along particular paths and flows. It would provide compelling evidence for the structure and behavior of dark matter on cosmic scales. There is also the possibility that these galaxies are linked to exotic astrophysical processes. Some hypotheses suggest the existence of previously unknown gravitational slingshot mechanisms capable of imparting immense velocity to entire stellar systems. If new classes of events, such as interactions with rogue supermassive black holes or large-scale gravitational waves, are discovered, they could help explain why some galaxies achieve such extreme speeds. Investigating the environments around these objects could reveal whether they originate from regions of high gravitational instability. Another avenue of research is whether high-velocity galaxies represent a previously unknown evolutionary pathway for galactic systems. Some galaxies are ejected from dense clusters or experience prolonged high-speed motion through intergalactic space. They may undergo unique evolutionary processes. A galaxy moving at extreme velocity might lose its gas more rapidly, reducing its ability to form new stars. Over time, it could evolve into a dark, inactive system, devoid of significant star formation. If astronomers identify quiescent galaxies that appear to have once been X, it could indicate that these stellar systems age differently due to their extreme motion. Another intriguing possibility is that rapidly moving galaxies could serve as natural laboratories for testing relativistic physics on a galactic scale. Since objects moving at near-light speeds experience time dilation and other relativistic effects, their internal physics may subtly differ from stationary galaxies. If ultrafast galaxies exhibit unusual energy distributions or unexpected cosmic ray activity, they could provide an unprecedented real-world test of Einstein's theories at galactic scales. The potential for these to reveal hidden cosmic structures is another key area of study. If they consistently move toward or away from specific regions of space, it could suggest the presence of unseen mass concentrations, variations in dark energy, or even exotic gravitational anomalies. Some researchers speculate that hyperfast galaxies may act as natural probes of the universe's invisible framework, uncovering structures that otherwise remain undetectable. Large-scale surveys mapping their trajectories could provide new insights into the hidden architecture of spacetime. The ultimate fate of these galaxies remains uncertain. If one is moving at extreme speeds, does it eventually slow down due to cosmic interactions, or does it continue accelerating indefinitely? If some appear to gain velocity over time, it might indicate interactions with large-scale cosmic flows or even hidden dimensions. Conversely, if they eventually decelerate, it could suggest that intergalactic drag, dark matter interactions, or unknown gravitational effects gradually reduce their energy over billions of years. If any of these galaxies were observed to vanish from astronomical surveys, the implications would be profound. Such a discovery might suggest that certain galaxies are crossing into regions of space fundamentally different from our own, potentially supporting theories of cosmic gateways, wormholes, or even the multiverse. If a fast-traveling galaxy were to disappear without a trace, it would be among the most extraordinary astronomical findings in history, requiring a radical reconsideration of cosmic boundaries. As technology advances, the study of ultra-fast galaxies is likely to become one of the most significant fields in astrophysics. The ability to track them over millions or even billions of years could help resolve some of the biggest questions about the structure and evolution of the cosmos. Whether they reveal new forces, uncover exotic physics, or simply challenge our understanding of gravity on the largest scales, these extreme galaxies could hold the key to the next great discoveries in astrophysics. If these high-speed objects are part of a larger, hidden structure within the universe, their continued study may unveil aspects of the cosmos that remain undetected. They could be following unseen gravitational currents, responding to forces beyond our current understanding, or even moving toward a final destination beyond the limits of observable space. Their behavior might be signaling the presence of undiscovered cosmic phenomena, making them one of the most promising astrophysical mysteries of our time. One of the biggest questions surrounding ultra-fast galaxies is whether their trajectories are entirely random or if they exhibit patterns that suggest an underlying order. If their motion aligns with large-scale structures, such as cosmic filaments or dark matter streams, it would provide strong evidence that these stellar systems interact with an invisible framework shaping the movement of matter across billions of light-years. Space surveys will be crucial in determining whether these galaxies follow specific paths or are simply the result of chaotic gravitational interactions. The possibility that hypervelocity galaxies are connected to large-scale cosmic expansion raises additional questions. If they are accelerating beyond expected limits, it could indicate that space itself does not expand uniformly. Some cosmologists propose that different regions of the universe may expand at varying rates due to fluctuations in dark energy density. If these high-speed galaxies are concentrated in areas of anomalous expansion, it might suggest that the acceleration of the universe is more complex than previously thought. Another potential factor influencing these fast solar systems could be unknown astrophysical events. While many are believed to have been ejected due to interactions with supermassive black holes or gravitational slingshots within dense clusters, there may be other unidentified mechanisms at play. If some galaxies reach extreme speeds without any apparent interactions, it could indicate the existence of new cosmic forces, undiscovered astrophysical explosions, or interactions with exotic forms of matter. A more radical hypothesis suggests that these galaxies might be revealing new physical laws that only become apparent on extremely large scales. In standard physics, galaxies should not be able to exceed certain velocity limits without external forces acting upon them. If some ultra-fast galaxies are moving beyond these expected thresholds, it could suggest the presence of an unknown force or even a modification of general relativity that applies on the scale of galaxy clusters and beyond. If confirmed, this could revolutionize our understanding of gravity and possibly the theory that unifies relativity with quantum mechanics. Some physicists even speculate that hypervelocity galaxies might be linked to quantum effects on a cosmic scale. While quantum mechanics typically govern subatomic particle models suggest that quantum entanglement or other non-local effects might influence galactic motion under specific conditions. If galaxies exhibit correlation, it could be evidence that quantum processes play a role in shaping the structure of the universe at macroscopic levels. Another fundamental question is whether these cosmic wanderers represent a natural stage in galactic evolution or an extreme outlier. If they continue moving through intergalactic space, they may undergo drastically different fates compared to those remaining in galactic clusters. Over billions of years, such galaxies might lose their ability to form new stars as they deplete their gas supplies, ultimately evolving into dark, inactive systems drifting endlessly through the void. If astronomers identify evidence of such dead ultrafast galaxies, it could reveal entirely new processes governing the long-term fate of matter in the cosmos. The notion that hypervelocity galaxies might reveal the limits of the observable universe is another compelling possibility. If some move so fast that they eventually vanish from view, it might provide direct evidence that certain objects can reach cosmic horizons beyond which light can no longer return. If surveys show that these systematically fade from observations at certain distances, it could confirm that they are crossing into regions where spacetime itself becomes inaccessible. This would offer one of the strongest proofs that the universe has cosmic boundaries where information is permanently lost. Future discoveries might also include the first direct observation of a high-speed galaxy undergoing a major cosmic event, such as colliding with another galaxy or interacting with an unknown force. If a fast-moving system is observed to change direction unexpectedly, it could provide direct evidence of external influences shaping the universe at its largest scales. Detecting a hypervelocity galaxy accelerating in real time would be one of the most extraordinary findings in astrophysics, as it would suggest that an active mechanism is continuing to increase its speed. As technology advances, the study of these enigmatic galaxies will likely lead to some of the most profound discoveries in modern cosmology. Whether they are natural phenomena, remnants of a past cosmic event, or indicators of new physics, they challenge our current models of how the universe operates. Their motion may hold the key to unlocking secrets about dark matter, dark energy, cosmic expansion, and even the fundamental nature of space and time. Whatever the final explanation, these high-speed galaxies are among the most significant objects in the search for the deepest truths about the cosmos. If these hyperfast stellar systems continue to challenge existing astrophysical theories, their existence may force scientists to rethink fundamental aspects of cosmic evolution, gravity, and large-scale structure formation. These galaxies could provide insights into hidden cosmic mechanisms that remain undetectable through conventional means. Their study might ultimately lead to breakthroughs in understanding the true nature of dark matter, the effects of cosmic expansion, and the possible existence of previously unknown forms of energy or matter. One of the most significant research areas will be analyzing the environments from which galaxies originate. If they are preferentially found in specific cosmic structures, such as dense galactic clusters, cosmic voids, or regions with unusually high dark matter density, it could reveal the conditions necessary for their formation. If these galaxies are disproportionately located in certain regions, it may indicate that large-scale gravitational flows, dark matter interactions, or even quantum effects play a role in their acceleration. Another crucial avenue of research involves the internal structure of ultrafast galaxies.